get my camera back on now. Oh, come on.
Steve, we can all hear your pain.
Thanks, Mike. I can't get my camera to come on. Stay on. There we go, finally.
That looks familiar.
I hope so.
Were you able to get the Kansas video working?
No, so what I decided we'll do is we'll just provide that with the link for the recorded session.
Yeah.
So everybody will be able to hear it individually on their own computer then. I just didn't seem to get the option to be able to click on it. Okay, everyone. Well, it's 1:25 Eastern time, and we're on our schedule here. So the next part of the peer exchange is going to be on vendor and agency updates. We're going to have uh, Contour, which used to be 3D Radar, Mike Heitzman and Jacopo Sala presenting, and I will share my screen. Hopefully, everybody can see Mike's presentation. So go ahead, Mike.
Well, good afternoon, everyone. This is Mike Heitzman. I should say good afternoon or morning, depending upon what part of the country you're at. My name is Mike Heitzman. I used to be an FHWA engineer and know a number of you through my career with FHWA, then with the Iowa DOT, and then with the National Center for Asphalt Technology. I'm going to be doing most of the presentation, and then Jacopo Sala is going to come in to give you some of the meat of where the Contour Examiner software is currently at. Next slide, please. Some of the things we're going to cover in this quick presentation is a little bit of an overview on stripping. I know we've been talking about it quite a bit. Let's make sure we're all on the same page. Then we're going to do a little bit on 3D GPR basics. I believe there are a number of individuals on this peer exchange that are not familiar with it, so I want to go through some of those basics. Then we're going to talk about how GPR can detect anomalies, and I'm going to use that word in particular because we can't necessarily guarantee that what that signal reflection is actually stripping, but we can certainly say that the material properties below that pavement surface have changed, so we call those anomalies. We will talk a little bit about how to collect good field data, how that data is then examined, and an area that we as a highway community have not really given a lot of thought to yet is how do you report this information so that the design engineers and the rehab engineers have some information they can work with. And the closing two slides, we're going to provide a couple of thoughts to the pooled fund state panel as to how you might proceed with some of the concepts of a multi-state field survey and the multi-team data analysis concept. Next slide. So we've all talked about stripping. In general, we are talking about the separation of the asphalt binder from the aggregate, and we need the presence of moisture to do that. In some cases, we have very limited stripping or minor stripping where there's really no change in the material density or characteristics. It's just not adhering anymore. More commonly, what we saw in a lot of the cores earlier on from the states is that you have some severe stripping to where you certainly have mixture strength reduction. You could get rutting. I've been in some of those places in Iowa when I was there. We can certainly have displacement of the aggregate within the mixture, and that's why we get some of that shoving and moving around. And I've seen some very significant mixture layer movement, but it's typically not that surface mixture. It's going to be a mixture down below that has the stripped issues. So we need to understand that the stripping is caused by the chemistries of both the asphalt binder and the aggregate. We try to address that as much as we can at mixed design time, but it does still occur because we don't always get positive test results to work with. We have to have the presence of moisture. So you may have a layer looks perfectly good for a couple of miles, and then another half a mile or so, you have a lot of issues because of the presence of moisture in that particular area of the roadway. I've also seen, and I've talked about hydrodynamic pressure of the vehicle passes, which can certainly accelerate the damage. Next slide, please. When I was going through this in review and preparation for this meeting, I decided, well, really types of stripping probably isn't the right title. It should be locations of stripping. And with that in mind, a lot of what we see is a poor lift within the mixture that strips out. But we can also have transverse crack bottom-up stripping, where the moisture gets into the crack and it begins to build damage from the bottom up. We can have certainly stripping caused at the longitudinal joints where we typically do have lower mixture density, which then allows the water to get in even further. And then we also have just stripping due to hydrodynamic pressures. And back to one of the state's issues on putting AC over concrete. Yes, you can literally put a impermeable base underneath that asphalt and trap that moisture in there, which then the hydrodynamic pressures then get into um, a stripping situation. What I do want to distinguish too right now is that in the Sharp 2 effort, we were looking at delamination as a general term. What we're talking about today is stripping within the mixture and not the debonding between two layers. That generally is not a stripping issue unless you start to have the actual lift layer come apart. Next slide, please. Okay, moving on from stripping into ground penetrating radar, there's a number of different types of ground penetrating radar that are in use. A very common type is the impulse-based system, which some of you are very familiar with. There are others like noise modulated, frequency modulated, but the one we're going to focus on is the stepped frequency contour 3D radar. The reason this is important to understand is that the stepped frequency allows us to do both high and low frequency measurements, not necessarily simultaneously, but in steps. And what we are able to do then is high frequencies give us very good resolution, but they don't travel too far into the pavement. So by having the step frequencies, we can essentially progress from high frequencies for better resolution at the pavement surface into lower frequencies that give us better information as we get deeper into the pavement. Next slide, please. So the 3D radar system that's available through Contour. It is a GPR array, which means we have a whole series of the antennas along the width of the antenna array. And each one of those then has stepped frequency capabilities. And by having the array and the step frequencies, we can get both optimal resolution and penetration into the pavement. This is, in my opinion, the best possible GPR data, which can look at the entire pavement as a whole and not simply single lines from some of the typical 2D radar systems. If you couple that with a very accurate global positioning system, then you have a very accurate position of where your damage is at. provided we can find it with the reflected antenna signals. Examiner is the software package that takes this very large database of GPR data and processes it into something that for us as engineers, as pavement engineers, we can actually understand what the information is telling us, because it's giving us a visual cue and not simply that vertical profile of the GPR signals. Next slide, please. Very quickly, in the illustration in the upper right-hand corner, typically that 3D GPR antenna is mounted to the front of the vehicle. Although you did see some pictures of other methods of mounting. There are 3 antennas in the lower left-hand portion of this slide. The one that's in the forefront is the air-coupled antenna, which we will spend our time on. Behind that is a ground-coupled antenna, which is more typical for bridge and utility work. And the one that's in the background there is a deep penetration antenna. We're not interested in those today, but they are a part of this overall system. The little black box just to the left of the laptop is called the geoscope, and that is essentially the heart and soul of developing all of the signals that are being processed through the antenna. Next slide, please. So with an air-launched antenna array, we have a number of things that we're able to accomplish. First, it does do the ultra-wideband antenna elements, so we get the step frequencies. Those channels, those little antennas, are only 3 inches spaced apart as you go across the face of that antenna. Because it is an air-coupled system, we are able to do the surveying of the field at high speeds. So generally, you're going to be able to move at the normal traffic speeds and not have to deal with very slow movements. The rest of the information is important, but down in the table, which I know is difficult to read, basically this antenna can be purchased and used at different widths, essentially widths of the antenna. Very common, what we've seen so far in the highway community is either a 1.8 meter antenna or a 2.1 meter antenna. Everyone is a little uncomfortable getting an antenna that extends beyond the sides of the vehicle. But those 2 antennas, generally with 2 passes, you can in fact measure the entire pavement. Keep in mind, regardless of the antenna width, we are still getting in individual antenna channels every 3 inches. Next slide, please. Here's a couple of examples of the mountings. The one on the left is from Texas, and the one on the right is from Minnesota. That happens to be the FHWA van that was then is now being used by Minnesota. Everyone has got their own mounting systems at this point, and part of that's because of the types of vehicles they may be using. Next slide, please. Just to give you a little bit of a sense on this issue of high frequency, low frequency. On the upper left side of this graph, you see that red sharp line. That would be a high frequency 3 gigahertz antenna. While I get very good resolution with that antenna, because of the high frequency, the penetration in the pavement is very limited. On the other side of the spectrum, if I have a low frequency antenna, which is in this case only 250 megahertz, I get very good penetration into the pavement, but the resolution, because of the size of that frequency of the radar, the resolution isn't as good. The geoscope, which is the blue line in the center then, because of the step frequency, allows us to get the best possible resolution for a given depth. And that is one of the great values of this system. Next slide, please. To give you a sense, in each one of these 3 cases, the antenna is moving from left to right. And on the far left, we have basically that 3-inch spacing between the channels. And then we're taking a reading every 3 inches. So you're getting extremely dense, extremely dense grid of data, and each one of those red dots, you are getting all of the stepped frequencies within the test. As I move towards the right and you look in the center, by changing the trigger spacing, I'm now essentially getting about 50% of the data, and I'm spacing out where that data comes from. And if I go to the far right, now we're at a 30 centimeter grid, and we're not getting as much information. And I caution everyone on using a larger trigger spacing simply to reduce the amount of data collected. You're going to want to have that good data, which in fact will be available in that dense array of information from GPR. Next slide, please. Another part of the settings for the field surveys is going to be the dwell time. How long does the system stay on each stepped frequency? The longer I can have that time, the better, but the longer that time, then the more time it takes for the system to go through all the steps, and it slows the system down. So one of the things in developing this pooled fund will be having some idea of what's going to be the best dwell time that would be used for each one of the surveys. Next slide, please. And this all boils down in the field as to how much data are you collecting. And yes, it is a lot of data. So one of the things to understand is to have a system which best collects that data. You can set the settings to where you have one data file, or the file can be set up to where you have a maximum output file. And what we are recommending generally is that the output files be no greater than 500 megabytes. As a general rule at the bottom of the slide, you can assume that for every mile, a single pass of the 3D GPR antenna will generate about 1 gigabyte of data. So under this scenario, if we use the 500 megabytes, then you basically have 2 files for every mile for a single pass of the antenna. Next slide, please. This is a very general view of what the examiner will provide you as far as when you're looking at the data. And the view the large view, the gray view that you have there essentially is similar to what you would have with a single horn antenna. But because we now have the 3-inch spacings, the view to the right is actually the cross section of the pavement, and the blue view below is actually a plan view inside the pavement at any depth you want to select. So with this is the basics of what examiner will be able to display to an engineer. I'm going to pass this presentation over to Jacopo to talk a little bit more about the details of the examiner software.
All right, can you guys hear me?
We can.
Excellent. Well, first of all, thank you, Mike, for taking care of the difficult part of the presentation. I'll take gladly the easy bit, the couple of slides. I want to mention, first of all, that it was very interesting presentations today thus far, and hearing what problems you guys are facing, how they manifest themselves. And although, you might call it stripping, it starts and it starts from many different points, from very, very different kind of materials, so very different causes in many cases. And it also becomes very many different things. That definitely helps us in finding methods and algorithms that exploit our data. And that really brings us to the software, because the software is the key. We have a system that collects a lot of data, as Mike was saying.
Yeah, it's okay. Yeah. It's just
so the
can you send please my reconciliations?
I don't know who has the mic open, but if you can please
mute.
Well,
we don't have a statement because it was not transactions. I have to fill up this.
All right. Okay, so that brings us to the software I was saying. We collect very dense data. We collect a lot of data, and I can tell you that from all the experimentations that we've done, starting 2008, I can't remember the first time I was working with Mike in Alabama. Then, we've seen that basically you need a high density, and that's because what we are trying to image in the asphalt is very subtle. So the more points you have, the more the easier it is, the easier the image is to read and therefore to interpret, right? So we don't have just a lot of 2D channels, we have a three-dimensional system, so we use the input altogether. And the examiner is built around the three-dimensional data. So here you're seeing the display. So if you want, this is the traditional way to look at three-dimensional GPR data. You would see different sets of data cubes. You can interact with them, you can annotate, you can trace interfaces, and you can display the results in a map, for example, like on the top panel there. And this software is built to handle very large data sets. So it doesn't have any definite limitation to the file size you can analyze or to the overall project size that you can analyze at the same time. What we are working on right now is really to, once you have analyzed this data, once you have interpreted this data, is to reduce the data and get only what you really need, because out of a very dense data cube, you don't really need the entirety of it. And this brings us to the next slide. I'm not really reading the points. Those ones, you guys can read them. I'm more sending my thoughts. And this brings to the latest things that we've been working on. So this pavement analysis, this is a set of tools that builds not on the GPR data, but on the interpretation. So, and this is very close to what Eyab was showcasing in his presentation. So once you have interfaces, the top interface, the bottom interface, you want to see the amount of activity in between. This is also something that Cam Mazer had been working on in previous iterations of finding stripping and delamination within GPR data and within 3D GPR data. So basically, you want to see the activity, you want to see the noise, you can call it as you want, but you want to see if there is anything that is anomalous in between a given subset of the data, and that subset is defined by interpretation. So top layer, top interface, bottom interface, defining a layer. And what you're seeing here is another way to visualize the data. So apart from the top right panel, the rest is just areas where you have potential stripping. So those purple areas, if I remember correctly, the blue would be where the layer is too thin. The purple area would be where you have some activity that is unexpected in between a layer. So that is highlighted, and then you have a simple slider to saturate or desaturate that image. Where do you stop it? Where it's still a little bit subjective. It can become quantitative, hopefully one day, but for now it's a qualitative approach. But the expertise of the structural engineer, of the pavement engineer, will make it so that once you have the picture you expect, you will stop moving the slider. And then what we can do is that we can diminish the overall size of the data and bring it on. So the project, as it is now, you could actually remove completely the radar data and bring it from a size that is gigabytes to a size that is megabytes. And those sliders will still work because we have done a sort of a summary in the background of the radar data contained in the layer. So you can still analyze those data, and you can store it with a couple, 2 or 3 orders of magnitude less in terms of size. And it is georeferenced. It has all the advantages that we had with the previous visualization, which was the entire data cube. All right. So we're trying to work in this direction. We are sensible to the input from users and current users, future users, and never to be users, but people with a problem to solve. And one other thing that I want to mention very quickly is that Examiner also has a door open to some customization. So anybody with a minimum amount of programming skills, or associated with a university or with some research group, can program and their own algorithms and embed them in our software without the need to to reinvent the wheel in terms of visualization of large data sets, which we have. And I think that was it for what I wanted to tell today. I guess I'll send the ball back to Mike.
Thank you, Jacopo. So some things to consider when you want to get a successful identification of anomalies. One of the things that hasn't been talked about yet today, but we need to talk about, is moisture is a key to identifying those reflections. And we've had experience, particularly with Caltrans during the sharp days, that there was a project that had very high reflections, and we were able to identify the damaged anomaly. It was in fact stripping, minor stripping. But when they went back to survey the same location during the dry season out in the desert, you could not find anything. So moisture is one of the keys. And I'm going to suggest to the group that, if at all possible, you try to set some boundaries up for trying to collect data after rain events, so you have a better chance of identifying some of those anomalies. I do recommend capturing the entire the entire pavement from one edge to the other, left and right, so you can get all the good possible data, because you really don't know where that stripping is going to occur or where it started from. We do recommend a 8 to 10 millimeter test spacing. At that test spacing, you are able to do things at normal vehicle speeds and without losing the good dense data that you have. The other thing which has come up and is a good practice is that you try to have a small section of pavement that you know is in good shape, or you know what's there, and you run that quickly to see whether or not the GPR and GPS systems are working correctly before you actually try to survey an entire project. There's no sense in getting 10 or 20 miles worth of data only to find out later on that the system was not working correctly. Next slide, please. As far as the steps for identifying the anomalies, this is a fairly basic set of things. First, you have to stitch all the field data together. You identify those pavement layers, and you try to suppress some of the external noises that might occur along the length of the pavement, particularly from cell towers and things. You establish a section of pavement that you think is a good sound pavement, and you define that as your normal pavement. Then you ask yourself a question: am I going to try to focus on a specific layer, or do I want to look at the entire asphalt pavement itself? And if you have a full depth asphalt pavement, you may have to do maybe several scans depending upon how much depth you have. Perform your anomaly scan. However, whatever software, whatever algorithms are being developed, then go back in and look at several of those within the data to see whether or not you have too sensitive or too little sensitivity, and then you report your anomalies. Next slide, please. Reporting is going to be important, and I do suggest that the pool fund states get together and decide what you want to report, so that all of the participants are reporting the same way. What I'm showing here would be an X, Y, and Z for location, but then you still have to have the area and its severity, and you could use that as a comparison of the value to a normal pavement, similar to what Eob was sharing earlier on. And you have to have a summary log. Keep in mind that a summary log may not have all the information that a rehab engineer would need, but this would be a good place to get started. Next slide, please. So a couple of suggestions to the panel as well. The states are going to have to be responsive to the field GPR equipment when it shows up. If they want to try to meet a certain weather event, the state's got to be ready for that. Used the same field equipment for all of these projects if possible. Yes, that means traveling around the country, but at least you eliminate one variable. Select projects that would reduce travel time. When I was an engineer in Kansas, I had projects on the east and west side of the state, and it would take me a day just to drive from one to the other. So trying to get two projects that are reasonably close will help. I'm suggesting, and we're suggesting, that a 10-mile project be a maximum project length that you should use for this particular study. If there is going to be traffic control necessary because of the state, then I would recommend that the state coordinate that. I've been in other types of projects where the state puts that on the burden of the surveyor, which makes it difficult. If you do have your own equipment, then I would suggest you run it at the exact same time that the pooled fund equipment is in there. And do obtain some field cords. They are needed in order to quickly validate and verify what the condition is of the pavement. Next slide, please. As far as the software development, these are very large project files. Data files in particular, so there's going to have to be a good system, a sound system for transferring those. Smaller the files, the easier it's going to be to transfer. Establish some standard filing names so that everyone's working off the same understanding of where these files came from, and all individuals should be using the same version of Examiner. And I know that you'll be able to work with Contour to make sure that you have those all the same current version to work from. We're not recommending that you export GPR raw data. Simply to work on the software, try to work within Examiner. And with that, Steve, I think we got just within the 30 minutes. We could possibly take one or two questions.
Looks like
Yes.
Eob has a question, Steve.
Okay, Yob.
Mike, Jacobo, thank you very much for this great presentation. I really enjoyed it, and I hope you continue to support and be involved in this project study. And thank you for the recommendation and suggestion. They are all on point. One thing, moisture, yes, before I was trying to be fast. Yes, moisture is an important. Thank you for touching on that. In fact, some of the laboratory testing and the field testing that we will be doing at Mill Road is specifically towards understanding the effect of moisture and the different pavement geometries on the capability of GPR to detect stripping. So yes, we will be we would like to be very careful on understanding at what moisture conditions you get good result. And then the second thing is if you can just show slide 16, Steve, would you be able to? So ideally, this is exactly where we hope to end up with a software that tells you, okay, these are the areas with anomalies or with stripping. But the pool fund study will also be able, in our view, to validate and verify what is the accuracy of these predictions and give some thresholds, some limits, whatever range. But ideally, this will be something that we will end up and then back it with verification, with validation, and also with some standards that tells you this is what's going to happen. One question that I have, these were comments. One question I have, I know you suggested that it's better and correctly so to use only one system for testing. But just in case this is not possible, can you give us an idea of how many 3D GPR antennas are in the states, and or if there are other ways for the states to secure the service?
I'll take a brief stab at this. I know we have some of the other Contour staff on this peer exchange as well. There are a small handful of states that have their own systems. California, Texas, Minnesota come to mind. There's also a handful of consultants that have the system and are certainly available to do these types of tests. My point in the slide was to try to eliminate any variability or eliminate one possible source of variability by using the same equipment in order to be able to compare one state's data to another state's data. I don't know that I can give you an exact number, though. That's something that we'd have to get from the other Contour staff.
Yeah, definitely. And one way could be that, or other way could be have all those GPR systems come and test at the same place, for example, in the mirror testing facility, so that we can have some way to calibrate or somehow to have a baseline difference between these different GPR system. Yes, but this is helpful. You're saying that at least 3 states they already have it, and then there are consultants that could help with the data collection efforts.
Right, and one of the other things to keep in mind, even everyone may have the exact same GPR antenna and geoscope and software, but the means by which that antenna is mounted to the vehicle will have an impact on the reflected signals that come back. So if you have 2 different antennas on 2 different vehicles, you may get differences in those signal responses because of essentially the noise that's generated by that mounting system.
Definitely, and we would like to capture that in this Polfan study, because one of the things we would like also to have a standard testing procedure where it trying to standardize that. Definitely, yes, that will be. Thank you, Mike.
Thank you.
I would also like to add very, very quickly that indeed, AOAB is absolutely right. So we need verification and we need more data to be able to make the system as semi-automatic or automatic as possible, and to really narrow down the issue that we are trying to detect to, in the best possible way. And the only thing we can do is really to provide you a software that can already eat that kind of those kind of algorithms, and I think we do have it. So I'm very happy that we are involved with this within this study. Mm-hmm.
Yeah, and this will be a collaboration between some states providing the data, between vendors and others consulting, providing their knowledge and the expertise. So that's the ideal format that we are hoping to achieve. Sorry, I think it's someone with question. I think I have a question, Mike, Steve.
Okay.
Yeah, I just have a quick question. Jakob, good presentation. Thank you for doing that. So just look at the slide 16.2. So was that from the ground coupled antenna or air coupled antenna?
That is an air coupled antenna. So it's yes, correct. Mm-hmm. Okay, good. We could apply to also the ground coupled. The granularity of the data is a little bit different. So
we don't have these versions of software, right, Jacobo?
You should have it. It's available in case, but please do get in touch if you don't. Okay. So at least I can.
Yeah. So that's another thing. That was another question I was going to ask you. So you said a person with the minimum programming skills can input what this code into the examiner. Is that what the minimum skills you talk about here? C++, C sharp, or?
Oh, actually, it's for standard algorithms. Like I want to go through the data and make 2 + 2, just to name an operation. You just need to know how to program for loops. Then you can do it directly in C#. But actually, I can also tell you that I tested recently that you could program in another language, like for example Python, and then launch Python through certain commands in the. I might make an example of that. So if you guys think it's useful, just let me know.
Yeah, that may be good for provide us training later on, just like it did before. We should continue as training on the 3D radar sometime. Last question is the picture showed the stripping. That's only, I know Kane developed the method. That only tells the XY location, right? Does not tell you the depth of stripping, correct?
No, correct. It tells you the location. That's correct. X and Y. The depth, you know it more or less because it's within a. You selected a top interface and the bottom interface defining a layer, so it is in between there.
Okay.
Yeah. but we had a little bit. Well, we could discuss. We could discuss that. We could output the depth, but it's a bit shaky.
Yeah. Okay. Good.
For
Thank you.
Okay, Mike and Jacopo, thank you very much for your presentation. We'll move on to ARB Systems of America, TSD and 3D GPR radar, and that'll be Jerry DeLeyden.
Do you want me to share my slides, Steve, or you want to just flip through the slides and I'll just narrate?
I think I got it up for you now.
Deal. Thanks, Steve. So I appreciate the opportunity to kind of quickly run through what, as I understand it, our role might be in this study. Most of you may have already seen a lot of these slides if you've been involved in the TSD pool fund study, but I'll quickly go through the technology just to make sure we're all on the same page. So next slide, please, Steve. So the three things, we'll talk about the technology, some of the case studies, and then address questions and discussion. Next slide. So, you know, it's interesting to me, some of the discussions that we've heard coming up to this, you know, imply that everybody already knows where the stripping is. You know, the reality is, as we've been testing thousands of miles, we're discovering things that people wished we wouldn't have discovered. You look at a section like this, it looks beautiful really from the surface, which is a testament to the maintenance engineer that did such a great job of maintaining it. Next slide. When we drive over it and discover there's issues, I like the way Mike phrased it, but you know, the reality is we never know exactly what's in there. Most of the people, when we tell them we've identified some issues, they're very quick to go out and do the forensic work. In this particular case, you know, two cores 5 feet apart show very different pavements. So, you know, it's intriguing to me, having been in this business for 40 years, that people say that we should just focus on the bad pavements. I don't know how you do that. You got to look at all the pavements, but we'll get to that here in a little bit. So next slide. The whole idea of this technology, ARB Systems is a systems integrator. We're basically recognizing, acknowledging the fact that people need to do more with less. So let's just put any system that we can think of on a platform and collect everything simultaneously. When we brought this device into the US in 2016, pool fund study was started shortly after for much the same reasons as this pool fund study, to kind of explore how do we apply this wealth of information. And one of the outcomes from that pool fund study was, you know, what would be cool is if you could add GPR to the truck, because it would help complement some of the other data streams. And in fact, as you'll see here in a little bit, we have now added the contour 3D GPR right there where the dolly wheels are in the middle of the truck, so that we can collect it along with the other structural response, all the surface characteristics, the right-of-way imagery, so that you have hopefully all the information that you need really to make an informed decision. Next slide. So in 2020, from the TSD pool fund study, we added a series of upgrades to enhance the lasers, improve the right-of-way cameras, things of that nature. And then, like I said, in 2022, we added the 3D antenna to start also including in the output of our Passover projects the inclusion of all the GPR data as well. And I fully intend, or anticipate, I guess I should say, from, if not just from the TSD pool fund study, but hopefully participation in this one, that agencies around the country will now start to have an opportunity to better understand some of the limitations we've been talking about here, about what settings should be used, and that's obviously going to depend on what you want to try and achieve with it. The objectives of this study are very, very specific, but a versatile antenna like this can accomplish many different things, and knowing how to use it is a huge part of the learning process. Next slide. So the other piece of this that many people touched on, I'm trying to go through quick because I know we're trying to catch up. These systems are capable of collecting massive amounts of data. Everybody's already got 16 jobs they're responsible for. They don't have time to start becoming an expert at analyzing all this data. So you really need the tools to facilitate that implementation application process. All of the data that we're collecting is, we put it on a cloud-based server so that you can access it through this viewer. I mean, we also do provide the raw data to people if they want it. But, having a viewer that can quickly drill into the data sets certainly facilitates this implementation process so that you're not just buried in data. Next slide. So as an example, one of the features that was quickly pointed out, added, if you will, one of the folks said, Jerry, you're collecting all this stuff. Can you just tell us FHWA good, fair, and poor for map 21? Because all of our software developers are down under in Melbourne, when the suggestion came in, we sent it off to Melbourne. By the time they started their day, the end of our day, they were able to program everything that was needed. So the next morning when the person that suggested it from Idaho got into his office, we'd already added a filter so that all you had to do was enter in the criteria you were seeking, and it would create a heat map that showed, highlighted, if you will, those areas. And I think someone asked here fairly recently, could you do the same thing for identifying stripping? And I believe, based on listening to Steve and Ian, the intention of this pool fun study is absolutely to create that kind of algorithm. Then we just add it into, the viewer, and you select that tool and it will show you those locations. We already have a similar feature for doing segmentation of projects, and we've had various agencies that have kind of used the GPR data to segment out areas of concern. So there's a lot of things that can be done with a viewer like this without really any effort on anyone's part. Next slide. So just real quickly, I always like to kind of go through some of the examples of how to use these volumes of data. Most people assume that when it looks bad at the surface, it's probably bad structurally. The reality, unfortunately, is that if you have to wait till it looks bad on the surface, by the time you put in all your requests for funding, it's going to deteriorate significantly by the time you actually get the funding and get the plans drawn up. So, we're really trying to see beneath the pavement surface to identify areas of concern before they propagate to the surface. And then the example on the far right is the other interesting extreme, which is when it looks horrible from the surface, but when you have all of the appropriate data, all the structural response information, quite frequently you discover that there's actually no structural problem. It's just a bad surface mix, and all you really needed to do was mill off the surface and replace it. So between those three cases, if you can adequately sort these volumes of data in an efficient fashion like this, you can pretty quickly get to what treatments are needed and why, and if not eliminate, at least significantly reduce the amount of destructive sampling and what have you that might ordinarily be done. Next slide. So, there's already been significant discussion about how to apply such data, and I do think it's kind of interesting to think about how specifically this data can be used for identifying areas of stripping. We definitely, ARB Systems does not intend to be doing the analysis of the GPR, which I think makes this kind of an interesting project to participate in, because I want to be agnostic and just let whoever wants to analyze the data. To that end, Ken Mazer has shared with me, if you will, some ideas, suggestions of work he has been doing with this data for some of the agencies we've been collecting data for and talking with. And he's essentially using the TSD data to help complement those analyses. Next slide. One of the examples he shared was, very similar to the others we've seen. He did some work at NCAP and started to identify the locations. So I have a fair amount of confidence, particularly after listening to this discussion, that there should be multiple people who could analyze these files. The other, I think it's really important from the work we've done with the TSD to focus on some of the discussion that has been started here about standardization of the data collection process, because it really shouldn't matter whose antenna is being used or, those types of things. There should be specific settings for the objectives you're trying to accomplish. And if not, then, we still have a lot of work to do to improve on this technology. Next slide. Here's another example that Ken's provided of a project he actually did in Minnesota. And again, demonstrating that there are, already in place procedures for using the technology we're talking about. Interestingly, there's a number of folks that have already acquired, the software that Mike was mentioning earlier, but, I'm one of those people that would like to keep an open mind that hopefully others come up with interesting ways to analyze this data as well. Next slide. Ultimately, and again, this is one of Ken's slides. It's kind of interesting. We just seem to be on the same wavelength because he provided these slides separately. But, I'm one of those people who is always looking for efficiency. We're all busy. We got lots of other things to do. A project like this can be, deemed truly successful if all you have to do is ask somebody to collect the data and they can start to highlight for you geospatially locations that you should be wanting to go back and look at. And I think you're probably a lot closer to that objective than you may realize. Next slide. Again, comments, having talked to we've collected data in 30 some odd states over the past 4 or 5 years. And it's always interesting the difference between the ones who want to do the network level evaluations, the ones who want to do the project level evaluations. It's usually a function of what division they work in, whether they're in planning or in materials. But the reality is we're starting to close this gap between network level and project level where, when you're collecting data continuously at traffic speeds, it's granular enough that you could take network level data and use it on project level applications. So hopefully people keep that in mind as they're starting to think about how they might want to pursue the approach for this project. Next slide. The key here is to really, to me, trying to find ways to be, less disruptive to traffic, getting this better understanding of the overall condition so that ultimately we're getting, more appropriate treatment selections that are saving agencies money. Next slide. I know that one of the questions that has come up, Steve, both asked the same question, just trying to compare this pool fund study to the TSD pool fund study. Obviously this one is far more focused in its objectives, which I think is fairly healthy, just to see, all right, if we drill down, can we identify specific tools that can be used with these data to answer the questions that we're trying to address. What I have suggested, just to avoid frustration and confusion, we have a very simplistic pricing structure for the other pool of funds study. If you are interested, I'm sure Steve can connect you to that or send you back to me. I think Brian Diefendorfer is going to be talking a little bit about it here in a bit anyway. But if both projects have the same pricing structure, then if you want to collect, you know, a half a day's worth of data for one project, or you really would like to see, you know, a multitude of projects, you know, to get the most money out of, you know, the day, you know, we can certainly come up with a way that'll make that very affordable so that people are able to get the data that they're interested in and then work with the pool fund study team to start analyzing the data sets that have been collected. Both of the studies provide for the data collection when and if desired, specifically to help agencies focus on projects they're interested in and not necessarily have to be working with data sets from a highway in some other state. They, you know, both are seeking very specific application strategies, although slightly different application strategies. And both are seeking to advance the state of the practice, because ultimately, you know, what we're looking for is a way to not only identify problems within projects we already have suspicions about, but problems in projects that, you know, we didn't even realize existed. You'd be surprised how many of those exist. Next slide. And with that, that's my last slide. I always like to leave people with questions to think about and ponder, hopefully provide feedback. My objective is to try and keep advancing the industry. And with that, I thank you. Hopefully I got you back on track there, Steve.
Yeah, Jerry, thank you for time. Okay. No new chat questions.
I just want to add that we do have a couple of states that are interested in this current pool fund study that have already collected TSD and GPR data, like Georgia and maybe Wisconsin. And hopefully we'll be able to see, look at some of that data in this current pool fund study. Otherwise, like Jerry, you said, we'll really love to work with you to have those other roads also collected and analyzed through both TSD and GPR.
Yeah, and when we heard what Ian was doing in Georgia, he said about all the other kind of testing that he's going to do. So that's interesting.
Yep.
Okay, well, that was a good segue into the next presentation. So thanks, Jerry. VDOT Brian Diefendorfer is going to talk about the pooled fund study on traffic speed deflectometer devices. So we have Brian here. I'll load him up.
Thanks very much, Steve.
Okay, Brian, thank you.
Hello to everyone. Thanks for the opportunity to come speak about the work that we've been doing. I'm here to share a little bit about some of our experiences with pavement NDE technologies, and in particular, the traffic speed deflection devices, in this case, the TSD itself. And this work is undertaken as part of a pool fund study. And unfortunately, I forget the number on it, but anyway, you can look it up. And Steve, next slide, please. What I'll do is talk just one slide here real quick about what we do in pavements in Virginia and why we think really the TSD is a way for us to move forward with structural testing of our pavements. We are one of the states that maintains almost everything from the interstates down to subdivisions. We have more than 128,000 lane miles of pavements, and a little more than 3/4 of those are classified as secondary routes. So these can be lower volume routes, but in a lot of cases in urban areas, they can be, 20, 25,000 vehicle a day pavements or even higher. In terms of our annual condition, we collect the surface condition. So, things you can see from the surface, cracking, rutting, that kind of information, collected on 100% of our interstate and primary routes every year, and 100% of the higher volume secondary routes every year, and then every 5 years on the lower volume secondary routes. So quite a bit of information, but again, it's all surface condition. Next slide, Steve. So I'm not going to get into much detail here because Jerry covered this pretty well in the last presentation, but I have this as reference in my presentation too on what is it? What's the traffic speed deflectometer? Next slide, Steve. So to me, looking at the TSD and these types of devices, there are several benefits to the agencies. In addition to looking at structural capacity at traffic speed, we can also look at all the other pavement distresses, the functional pavement distresses, or the things that you can see from the surface of the pavement. And to me, it really completes the picture of what's going on within the pavement system itself. Again, in my opinion, using a device such as the TSD allows for network level structural testing, which really would be almost impossible without some sort of traffic speed device for mainly safety concerns and of course the continuity of measurement or continuous measurements. Next slide, please, Steve. So the pooled fund study, and there's the number I couldn't think of earlier, TPF 5385. We are coming up on the last year of the study, and if there are enough states that are interested in continuing with a new study on the similar topic, we will certainly explore that. Right now, this study is, again, approaching its 4th year, and currently there are 25 state agencies plus federal highway involved in the study. So the objectives of the study were to establish a research consortium, which I think was done, where we can talk amongst each other, answer questions, and come up with new ideas. Provide agencies with guidelines on how to specify data collection and use, which I think is also has been done, and then provide a mechanism to conduct pilot demonstration testing. And so the big thing I think about this with most states, and certainly Virginia is one of those too, it's really hard to get this kind of testing done when there's only one vendor. It's in essence a sole source proposition. So going through a pooled fund study is allowing states to be able to do this type of testing and collect this type of data in a much easier manner than they could do it by themselves. So the pooled fund study had about 8,000 miles planned for 2022. And depending on the state and the number of days they wanted testing and the amount of funding they put to the pooled fund study, this ranged from somewhere around 200 to about 800 miles per agency. And this is kind of, I think Jerry had something very similar to this and some output data that you can see in terms of maybe some quantified results. This particular slice of data, I guess, looks at cracking percentages, layer thickness data from GPR, rut depths, deflections, IRI values, and so on. Next slide, please, Steve. So I want to talk a little bit about how we are conducting our current structural data collection. And then I want to get into how we anticipate or how we're moving towards using the TSD data. So between 2006 and 2008, we did a network level FWD testing on the interstate. That's been a long time, and we did not do it again because of how long it took and how difficult it was to do. And we only collected data every 0.2 of a mile on the interstate system. So a lot of gaps between data points. So again, the data, there's gaps in this process. We only covered about 5% of the network, and the data is quite old now, in addition to this test spacing issue I just mentioned. Next, please, Steve. So what we're really following with the TSD implementation is the way we implemented the FWD data. In our PMS, looking at the surface condition of the pavement suggests 1 of 5 treatment levels based on surface condition, and they range from do nothing all the way to reconstruction. And within each one of these, I guess in the preventive, corrective, and restorative and the reconstruction options, there's a whole slew of fixes that can be chosen within each one of those. But the PMS recommends one of these 5 levels. So as far as with the FWD data, the FWD values in the traffic level were used to modify the treatment level. So we chose to either increase the level of treatment from, let's say, if the surface condition said do nothing and FWD showed a structural issue, we could have chosen to increase that level of treatment by 1 or 2 steps or keep it the same. And this is just a schematic to show the process. Again, all the measured responses on the left coming into a condition index. plus we have a series of decision matrices to come up with an ultimate treatment selection. So the dashed line box there on the left side of the image is kind of the previous process. And then coming from the right side, we have structural condition. In this case, maybe an example could be a good structural condition. We all call this an augmented decision process. And then there's a final treatment selection that includes both the surface condition and then also the structural condition. Next slide, please, Steve. So in terms of data collection in Virginia using the TSD, really in my mind, it's a new opportunity for us to realistically collect structural data across the network. As far as our data collection in 2017, we conducted about 4,000 miles or had about 4,000 miles of data collected on cross-state corridors, major corridors across the state, including most of the interstate system. And then in 2018 to the present, we've participated in the pooled fund studies, and we've had collected somewhere each year between maybe 500 miles, 1,000 miles, something like that. So a couple of the questions we came up with initially, what are some of the appropriate metrics? You know, some of those of you that are familiar with TSD data, there are different results that come out of it rather than from the FWD testing. So what are some of the appropriate metrics we should be investigating? Do we expect to see similar results to previous practice, in this case, FWD? And how often does the testing need to be repeated? So some of these things we're still trying to answer. Next, please, Steve. So this schematic just shows a blue outline is the outline, state outline of Virginia, and you can see the different colors going across all the different routes is our TSD result. And as Jerry mentioned on the last presentation, you can go through and scale that in their viewing software to where this can give you a color map of whatever information you want. And I don't remember if I did this in terms of smoothness or structural capacity or exactly what, but it shows you an idea of where we've done our testing. Next, please, Steve. So some earlier findings from work we did with a lot of folks at Virginia Tech, including Samer Katisha and Gerardo Flinch. If you look up and are interested in more information on this, you can Google VTRC report 21-R4. And we found that there was, in general, a poor correlation between structural and surface condition, which, again, shouldn't be a big surprise. Again, Jerry showed a good example of this with his photograph showing good surface condition, and who knows what was going on underneath. We also identified that the structural condition affects the rate of deterioration. So weaker pavement sections deteriorate faster, which again shouldn't be a surprise, but we were able to quantify that through the testing that we did. And then we did find that consistency in identifying weak areas was better between FWD and TSD than repeated runs of the FWD. So a lot of folks like to ask, well, does the TSD give you the same answer as the FWD? And in my answer, I suppose it depends what you're looking for. If you were looking for maybe a subjective ranking or subjective rating of the pavement, good, fair, poor, that kind of thing, in my mind, yes, it does. Next slide, please. So where we are right now, we've we started, I guess, last year, a study looking at implementing the TSD data. And the objectives of the study are to identify appropriate TSD data inputs, determine the time between successive tests, study changes in treatment recommendations, and investigate changes in financial impacts. And that last one is really huge because, again, if we're asking folks in our maintenance group to provide additional funding for TSD testing, they want to know, well, is it going to cost a lot more than what we are used to seeing for the pavements, or is it going to cost less? And so these are things that are important to answer. In terms of the data, we've collected TSD data for select locations around the state. And then we've gotten also GPR-based thickness traffic data from the agency, and then previous day temperatures, which I'll explain how we use that in just a second. Steve, please. So right now, the way we're looking at the TSD data, we are looking at it in terms of the structural evaluation by looking at the effective structural number and comparing it with the required effective structural number. And I didn't put any equations in this presentation, but I think most folks are familiar with the AASHTO 93 equation that lets you calculate that structural number value. So we calculate or determine the effective structural number, effective structural number from TSD measurements. And we look at the required structural number at 5 and 20 years using traffic data. And then we go through and compare the two, and we get some sort of idea of maybe perhaps a remaining life. So the financial evaluation, what's the difference in cost when considering the structural data? And well, the answer is, I guess it really depends. There are a lot of assumptions you can put into this, and we're just starting to scratch the surface on that. So I'm gonna leave that information for a later time, but there are you can really manipulate the data, I think, to make that financial outcome come in different ways. And I'll show that here in a couple slides. Steve, next slide. Thank you. So I put here a list of inputs that we need. So for the effective structural number, the inputs we're using a temperature corrected D naught. So that's the deflection at the center of the load from the TSD. And again, that's where we're using the temperature data. Pavement thickness from the GPR, and then we are not temperature correcting the D36 and D72 values and looking at the loading area radius. So once you have those inputs, that you can calculate the structural number effective. And then the required is similar, except we're coming up with most agencies have from their AASHTO 93 days, terminal serviceability index assumptions, reliability and design periods. We can calculate the resilient modulus from the information with the TSD and calculate the easels from traffic data. So in terms of the required structural number calculation, we can convert the traffic data to required easels at 5 and 20 years. Using the default terminal serviceability, reliability, and standard deviation to make that calculation. One way we can look at this is to calculate or view the data in terms of a structural condition index, an MSI or modified structural index, where we look at the effective structural number divided by the required. And so if your MSI is greater than 1, repair is not required. MSI is less than 1, repair is needed. And so how much repair is really needed? Well, again, it depends on some of your agency assumptions and how you calculate layer coefficients for various materials and things like that. Steve, could you jump to the next slide, please? And so this slide shows an example, and this is kind of an easy way to look at the data, but it doesn't tell you a lot about really what needs to be done. But you can see the data on the left side of the screen, kind of from 0 to maybe about 21 or 22 miles. A lot of that data is under an MSI of 1, so some sort of testing is, or excuse me, some sort of evaluation, rehabilitation is not needed. But if you look at the values greater than 1, sorry, less than 1, showing something is needed because the required is greater than the effective. You can see there's a big area of data between the 22 or 23 miles where no repairs are needed. And then again, a longer stretch between about 30 and 40 or 45 miles where some work is needed. Steve, can you go to the next slide? And I'll show another way to look at the data. Here's really looking maybe a better quantified way to investigate the data. Look at the structural number where we can plot both the effective and the required. And so the data here can be segmented. There are a couple of different ways we've done that within the pooled fund study, and I'll leave you to find that on your own. If you want more information, although I can direct you to it if you're looking for it. A lot of the data here between the 0 and let's say 200 mile post is showing that the effective structural number that we measured is higher than the required. So really no repairs are needed in that area. But if we get over towards, you see the 250 to 300 neighborhood or 300 to 350, you can see that the required value is higher than the effective. So some sort of rehabilitation treatment is likely needed structurally within that area. And when we're starting to look at here at the structural number of values, you can start to get an idea of what kind of severity of treatment, I guess, is needed. So if we have additions, a difference of maybe a half a structural number between the required and the effective, then you can probably equate that to maybe a little over an inch of asphalt or a change from existing asphalt. If we're talking asphalt pavements, existing asphalt pavements to new pavements, if you can increase the structural number enough, you can get an idea how thick that's required based on these numbers. Next slide, please, Steve. So again, we can look at, I showed here a couple of examples, how we can look at differences in structural number value. And if the effective is greater than the required, you can see some needed. I think I've got that backwards again. If the required is greater than the effective, you need some additional structural capacity. Remaining life is another way to review the data. And so we can call this a remaining structural life, RSL calculation. And we can look at that again using the AASHTO equation, and we can calculate the easels per year, divide the effective easels by the easels per year, and we can come up with this remaining structural life calculation. And so that's another way to view the data. Steve, next slide, please. And so right now, the way we're looking at this remaining structural life, we put some numbers on here to say, okay, if you have an RSL greater than 20 years, do nothing. And again, this kind of fits the same 5 treatment or similar 5 treatment categories that VDOT uses, although I'm being really generic here on preventive maintenance, thin treatments, thicker treatments, and reconstruct. And this is one of the places where I said, if you want to start to look at the financial implications by changing one or two of these numbers, where you define the breakpoints between the different recommendations, you can really change that financial output. And so again, the values here I have in that note depend on the assumptions and then even the comfort level of the agency on what they feel is the right move to make in a particular situation. And so here on this slide is an example. If, let's say, under a functional assessment, your response or treatment recommended was the thicker treatment, and your structural assessment, you have a range of possibilities, and then you can modify a decision to be where if you have, let's say, your structural assessment says to do nothing, maybe, or excuse me, to do a preventive treatment, maybe you do a thin treatment instead, because the functional assessment, you needed something thicker. But perhaps your functional assessment was really influenced by the surface condition, but the good structural condition exists. You probably don't have to do something as thick as that. However, again, with a caveat here, I'll put it as I did in the last slide, that these values really depend on the assumption that you'd like to make as an agency, and again, on the comfort level of the agency. But you can see pretty quickly, if you could start to modify these treatment levels, again, how you could really drive the cost differences by including the TSD data. Next slide, please, Steve. So in terms of a summary, again, we're looking to implement NDE technologies that can help agencies make more informed treatment decisions. And in my opinion, the TSD device is one of those. We can improve network performance, reduce lifecycle cost, and reduce environmental impacts by using this type of information. We also need to do additional research work on looking at optimal measured values or the calculated indices to use. And I gave a few examples here of ways it can be approached. We need to, again, continue refining the deflection measurement protocols and work on calibration efforts. I believe that's the last slide I've got. So thank you very much for your time, and I'd be happy to address any questions if there are any.
Brad, this is Ia from Minda. Thank you very much for this presentation. And here at Minda, we are very interested on this TSD pool fund. We are still having some internal conversation, but hopefully we'll come talk to you at one point. But one of the questions, just quickly. So I just want to make sure I understand correctly. When you have this TSD conducted at network level, do you then do project level investigation on areas identified by the project network level testing, or you have enough information to go forward, to move forward?
Yeah, that's a great question, and it's one we get asked quite a bit. In my opinion, now again, you could ask somebody else; they might have a different one. But in my opinion, I think we could use the use the TSD response now to look at network level testing. And to me, if I want to go back through and start doing design work, I would like to look at those sections that the TSD identifies as problem areas and do some follow-up FWD testing on it. Now, I say that because we're still looking at this process of calculating structural numbers using TSD data. I think we're very close to the fact, or very close to the point where we could be using TSD for project level investigation. And I think in my mind, once we get to that point, then that's really will really be maybe the ultimate use of that piece of equipment. So we'd be covering both project and network level conditions.
Okay, thank you. And then the other related, since now you're also collecting 3D GPR, I assume if you use all the high density data collection, I mean, first of all, that will slow your speed, and then you will have a lot of data to process and to store. How are you utilizing right now the 3D GPR data?
Right now, the vendor ARB is providing that to the agency, basically in a tabular format. So okay. I don't know if Jerry wants to comment on that further, but that's as much as I have on it.
Sounds good. Okay. So the states will be responsible in processing that data.
So based on Jerry's comments from the last presentation, ARB is providing all the TSD data to the agencies through the pooled fund study processed, except for the GPR data.
Okay. Thank you, Brad.
Yes, thank you.
I'll share a couple thoughts here real quick, just to make sure everybody's on the same page. But in my experience, having worked with GPR data over the past 40 years, I don't, kind of similar to what the comment Mike was making, I'm reluctant to just watch everybody pretend they're GPR experts all of a sudden. And with that in mind, I heavily emphasized to my friends at ARB that they should not be attempting to do this analysis. I think there's people who would like to try and do that, but I don't think that there's anybody at ARB that's really qualified to process GPR the way it needs to be done. So with that in mind, essentially what I've proposed and everyone's accepted is that we will give the GPR file to people for them to use as they see fit. When and if they're, we get a request to get the data analyzed, we'll connect them to people like Ken or Contour or whoever wants to do the analysis to make sure that they're getting proper analysis of that data. Hopefully that makes sense for everybody.
Yes, it makes sense. So do you give them the data segmented by roads, or you give them the entire data for them to cut or?
From that perspective, I know some of the states, even with the TSD data, have asked for it to be segmented out into different projects. That's not hard to do. I mean, we're data people, so segmenting it out into separate subsets is not a monumental exercise for us.
Okay.
But initially, for most agencies, they just need to have the file in case, as Brian can attest to, someone in purchasing is going to come and say, have you received the file? Do you have the data in your possession? And they need to be able to say, yes, we have the data. But most of them won't usually do much with it. They just want to have the file in case someone asks.
And I assume the 3D GPR you're collecting always at the same speed, and you're using the same parameters for all the roads. You're not changing those parameters, right?
We have not changed yet because, again, we don't know better. And I think, again, to Mike's point, Mike made some excellent points about, how and if and all those kind of things. I'm expecting through these pool of fund studies that all of the industry is going to learn a lot about what settings are appropriate for what applications and so forth. I know Ken and I have already had some of those conversations, but in my opinion, there's still a lot to be learned. But to your question, if someone says, "Hey, for our project, we want to set this way," who am I to argue? Okay, fine, I'll change it if that's what you want to do. It's not difficult to change the settings.
Thank you very much.
Mm-hmm.
Anyone else have any questions for Brian and or Jerry?
Steve,
Hey, Brian, this
has his hand up.
I'm sorry.
Brian, this is Dishun Taodai from Minda. Just a quick question. You, in the last slides, you mentioned about the calibration methods. Can you elaborate a little bit? You try to calibrate the sensor, or what do you mean by calibration?
So there's a ongoing NCHRP project, I believe it's 10105, that's going through that process right now.
Okay, it's just a calibration the sensor, or just calibration the whole equipment?
The system.
The system in terms of the measuring the structure number or deflection. No,
it would not be the structural number measurement, well, because that's a calculation. But it would be on looking at the deflection values.
There is actually an NCHRP project right now that is working on developing a standard for using these types of devices going forward. And essentially what they're trying to do is to make sure that the response from the device is consistent with the expected response for a given, pavement structure.
Okay, thank you.
I thought I heard somebody else have a question or a comment.
Mike Heitzman has one.
Oh, go ahead, Mike. Mike, I can't hear you.
try this. Is that better?
That's much better.
Okay. Brian, with your experience with the TSD pooled fund, I'm fairly familiar that FWD certainly responds different depending upon pavement and climate conditions. Did you try to set any guidelines for when the TSD data was collected during the pooled fund?
No, Mike, we didn't. And one of the reasons for that is the availability of the equipment. By being one device in the entire country, it was really, it's been difficult. And again, not to have Jerry answer every one of my questions, but it's been very difficult. From my seat, for them to be able to schedule and coordinate going to different parts of the country without hopscotching back and forth. And so really the climate, they've been trying to do the best they could in terms of climate of getting, southern states in the cooler temperatures of the year, and then northern states in the warmer temperatures of the year. But beyond that, it's been pretty difficult to be much more, maybe much more refined than that.
The reality is it's been very eye-opening because some states now have the luxury, if you will, of pushing the envelope. So Michigan asked us to collect data for them here within the past couple weeks, just to see if in fact it would look stronger when it was colder. And they had us test, earlier in the year to see if they could see a significant difference. I know that Rick Miller has had me do similar exercises in Kansas, and some of the other states are exploring the same thing. I mean, the reality is nobody tells trucks to stop driving on their roads, except for maybe the Canadian provinces. So it is kind of healthy to know the impact of climate on these properties.
Okay. Anyone else? All right, let's move on to our next presentation from Olson Engineering on impact echo and spectral analysis for surface waves. And that'll be for stripping. That'll be done by Pat Miller. And I'll load you up here, Pat. Okay.
All right. Thank you, Steve. Can you hear me?
Yes.
Great. All right. Thanks, everyone, for the opportunity to talk a bit about our system today. I'll kind of cover the system in general, the test methods we're using on the system, show you some previous results from this ongoing Sharp 2 study, and show you some recent developments as well as where we hope to go from there, and then open up to questions. So go ahead, next slide. So our system, we call it a sonic surface scanner, S-cubed. It's a slow rolling scanner for condition mapping of pavements or bridge decks. There's a photograph there of Larry Olson pushing the scanner on this project in the early Kentucky testing. Multiple DOTs are using the S-cube system for concrete bridge deck evaluation, so it is out there commercially. It works really well for that delamination mapping. It employs 6 displacement transducers on each wheel. There's 2 sensor wheels. There's the white wheels kind of in the center of the device. And those are the sensors that are going to measure the data for each of the tests. We're doing a test every 6 inches as the system is rolled along the pavement. We're doing both an impact echo test as well as a spectral analysis of surface wave tests simultaneously. So you'll hear me refer to spectral analysis of surface waves as SASW. Sometimes I may shorten it to just SW. I'm talking about the same thing. It just gets to become a mouthful. As far as the physics behind the method, the impact echo method, well, we're tapping the pavement surface with a little solenoid impactor. A little steel impactor reaches out and smacks the pavement surface. So that impact is going to generate a number of different wave fronts in the pavement surface. When we're talking about the impact echo method, we're primarily concerned with the P wave. So the primary wave, compression wave, sound wave, P wave, they're all the same name or different names for the same thing. That we're going to be measuring or interested in the P wave velocity. with the impact echo method, and that's related to Young's modulus. For the surface wave test, we're actually looking at a different wavefront. For the surface wave test, we're looking at the surface wave or Rayleigh wave. And that's related to the shear wave, which is also related to the shear modulus. So these impact methods or the acoustic methods are really looking to evaluate the condition of the pavement by learning something about the modulus and the material by measuring the velocity. Go ahead and next slide. This is just another kind of description of the wave, the physics behind the waves. The top plot there is the Rayleigh wave. The Rayleigh wave or surface wave only travels along the free surface. That's really the key thing to know about it. So it travels along that free surface of a pavement. It's a reverse elliptical motion, particle motion, and different frequencies penetrate to different depths. The P wave, if more people are familiar with, it can be a little easier to understand. That's that compression wave where the particle motion, particles get closer together and then expand back apart. And that's that spherical wavefront that's going out in all directions down into the pavement. Next slide. Just a further schematic of the impact echo test. This is kind of our handheld test method or test unit shown in the little picture. But again, it's a little tap with an impact solenoid and then a receiver measuring the displacement of the pavement surface. On a sound piece of pavement, we expect to get kind of a single nice reflection back from the backside of that pavement. If you have a flaw or discrepancy in the pavement, that's going to alter that reflection. This is showing some basic data from the impact echo method. The top plot is the time domain data. So it's time on the x-axis, amplitude on the y-axis, and that's the vibration data that's measured by the displacement transducer. The thickness, if you test a pavement, whether it's concrete, asphalt, any planar structure, the thickness of that structure is going to be related to the velocity of the structure and the frequency by that equation shown there. So we take this time domain data, we do a fast Fourier transform or FFT on that data to identify the resonant frequency of the pavement. And so that resonant frequency is really going to indicates the thickness, but it's going to be that resonant frequency that's going to shift either higher or lower if there's an anomaly in the pavement. Now, regarding the second test method we're employing, the SASW test method, as I mentioned, that's a different wavefront that we're looking at, but it's still the same impact, which occurs off to one side of one of the transducers. We're measuring that wavefront at the near transducer and then again at the far transducer. And what we're doing is we're looking at how that signal changes between those two transducers. So this is just a quick schematic of showing the impact in the two receiver positions. So the key element to the surface wave test is the surface wave, the Rayleigh wave, the surface wave is dispersive. And that the meaning of that term is that the different frequencies of that wave can travel at different velocities. And that's kind of a unique characteristic of the surface wave. So you have different frequencies traveling at different velocities, and those different frequencies are also sampling different portions of the pavement. The short wavelengths, the high frequencies, sample shallow near the surface. The longer those wavelengths get, the lower those frequencies get, the deeper they reach into the pavement. So you're getting a sample of a greater depth into the pavement. So this really is the key for the surface wave test, and allows you to develop a plot of the depth into the pavement versus the velocity of that pavement. This is data from surface wave test, kind of showing the flow chart of the processing. The upper two plots are the time domain data. So time, again, on the x-axis and amplitude on the y-axis from the two receivers. The left one being near the impact, the right one being the further from the impact. We look at the key parameter between those two measured signals is how the phase of that wave changes with respect to frequency. So that's that plot in the lower center is the wrapped phase plot with respect to frequency. And basically it's the slope of that phase that in the math comes out to be the velocity versus wavelength plot that you see on the right. So on the right, that's depth on the y-axis and velocity on the x-axis. So this is kind of a look at a single test point, looking at how the velocity changes with depth. And so if you have an anomaly in the pavement, you would expect maybe your top 3 inches, 4 inches is good. This is about, there's a change there about 4.5 inches, where you have a higher velocity for that 4.5 inches, and then you have a drop in velocity at, it could be a debonded layer or an area of stripping or delamination. That type of defect is going to drop that velocity. So when you're looking, I'll mention one more thing on the previous slide. If you're looking at the wrapped phase plot, the one in the center bottom area of the slide, we call that kind of the sawtooth pattern of the phase cycles. The wider the sawtooth is, that's higher velocity. So the tighter your cycles are, the narrower the cycles are, that's lower velocity. So if you're kind of just quickly glancing at a bunch of phase plot, the wider this, given a constant spacing, the wider the cycles, the higher the velocity. Okay, go ahead, next slide. This is just a closer look at the measurement wheels of our system. You can kind of see the sensors there, the brass sensors and the white measurement wheel. We line those up so that they're touching the ground at the same time. The little impact is off to the side of one of those sensors. And so we're impacting that pavement surface. We're getting the impact echo data on the near wheel. And that data is also used with the corresponding data from the far wheel in the SASW analysis. So it's one tap, both sets of data. We typically have those wheels spaced at either 6 or 9 inches, depending on how deep we're trying to investigate into the pavement. And then as we roll along the surface, we're doing a test every 6 inches. We do have the option to turn those wheels out of phase with one another if we only want to perform impact echo testing, and then we can do impact echo testing on each wheel alternating. But in that case, we don't get the SW data. Next slide. This is the basic data screen from our S-Cube system. There's a lot going on here. The far left is basically a thickness plot from the impact echo data along the test line. It's about a 500-foot test line. The top 2 plots in the middle are the raw time domain data. The bottom 2 plots in the middle, the one on the left is the FFT for the impact echo. The one on the right is that phase calculation for the SW test. And then the far right plot is that a single point depth versus velocity for the SW test. And so this is just showing one data point in the scan line. And so that on the far left plot, there's a little horizontal red cursor, and that's showing, that's the location where this data occurred at. And so you can review each test point if you want. So in this is about 530 feet of data, so we have almost 1,100 data points in this single scan line. Next slide. I'll just briefly kind of go through our some of our analysis procedures. We do have some automated analysis procedures as far as applying windows to the data to get rid of noise that may occur before or after the signal. For the SW analysis, we do want to focus on just the surface waves. We apply a window to try to eliminate some of the resonances that we don't care about that may be basically become noise in that process. So we apply different windows for the impact echo test versus the SASW test. Next slide. This again just shows the impact echo data, time domain from a pavement. This is an asphalt pavement now. This is time domain on the left, frequency plot on the right. This is fairly easy data to automate the analysis. We can have the program auto detect the signal and then perform the Fourier transform and then easily pick off the maximum resonant frequency. This is an example of kind of the output of that impact echo results. So again, it's a plan view heat map showing a single lane. This is data that was taken in the fall of 2016 on the NCAT test track, the original test track. We redid the testing with the scanner system after the scanner was fully developed, and in the fall with cooler temps to try to get kind of the best impact echo data we could on that asphalt test track. So this is a comparison of that heat map and those existing conditions where the light gray, dark gray, and brown are different simulated defects that were built into the pavement at different depths. So there was reasonable correlation between some of the defects in the impact echo test in this fall testing with the cooler pavement temperatures. Next slide. And so this again shows the wrapped phase plots from the SW test. This is the data that's more difficult to automate. If we get data that's shown on the left, very clean sawtooth cycles, we have algorithms that can really easily automate that processing, and we can pull that out of there quite quickly. But especially if you have anomalous conditions, you can start to have what we call glitches in that wrapped phase. So you see there kind of around 5,000, 5 to 6,000, 5 to 7,000 hertz in frequency. There's this glitch in the phase that we used a mask. The hash red is a mask to eliminate that piece of information from the data set. And that's the type of data that's more difficult for us to automate that we're still working on. Next slide. These are some example depth profiles from that NCAT track with varying conditions. The one on the left being the sound condition, fairly constant velocity with depth into the pavement. And then kind of progressively worse as you move to the right with drops in velocity. The two in the middle are around 0.4 of a foot, so around 5 inches or so. And then the one on the far right is a shallower drop, a shallower, more severe, larger drop in velocity at 3 to 4 inches down. We have seen that the magnitude of the drop in velocity is related to the severity of the defect. So this is, again, kind of the end result for the SW test, again, a heat map. Because we have information with depth for the SASW test, we're able to slice that at different depths. And so they're all the same plan view data from the same area, but they're sliced at different depths. So it's 1 inch increments from 2 inches through 10 inches. One thing, and again, then a few slides down, I'll show you again. So one thing we noticed with the SASW test is it is very temperature dependent. So I know there was previous discussion on the previous presentation about the rolling deflectometer unit I would expect would certainly have different results at different temperatures. We certainly saw that with the SASW test where the velocity we were measuring, which is effectively related to the modulus, was very different on a cold pavement in Colorado versus a hot pavement in New Mexico. So what we did was try to eliminate that variable. We plotted, took a histogram of the different velocities we were seeing, and then we normalized that by kind of the most common value in that data set. So this is just a histogram of the data. If you go to the next slide, this is the normalized result of that same data that was shown 2 slides ago on the NCAT test track. So it helps to kind of bring out some of the features, and you're not constantly fighting with your color scale as far as what velocities we should be using on a hot day or versus a cold day. Just kind of normalize it by that most common value. We can look at percent differences or relative changes from the average. And again, that's a comparison of the actual simulated conditions or as-built simulated conditions on the NCAT track there at the bottom. It's interesting to see that, for instance, the defect shown on the left is at 5 inches deep. In those top slices at 2, 3, and 4 inches, you don't really observe that defect, and then it starts to come in those kind of warmer colors at 5 inches and below. So it is able to detect different problems at different depths. The really shallow stuff at 2 inches kind of shows right off the bat at the top. Go ahead, next slide. So we did go out and implement this unit on at multiple different states. It was 4 states: New Mexico, Texas, Kansas, or I'm sorry, Kentucky, and California. And so these are just some photos from that field testing. We would typically do 1,000-foot section, and we were doing usually 6 passes on that lane. So at nominally 2 feet apart. Sometimes we'd scoot that last test line over a little bit to stay off the cones. Next slide. So this is, again, a typical result from those SASW results. This is from the Texas work. This particular piece here, this is a 250-foot stretch, it looks really good. This is normalized data. So obviously there's not much going on here. There's a little something coming in towards the far right of the plot. This, in comparison to the next slide, please.
Whoa.
Yeah, this shows an area where, okay, there's a lot going on here. So it's definitely, the system was definitely sensitive to changes, and it could definitely be used to say, okay, that, that first 300 feet of the project, no problem. And then beyond that, yeah, we got some issues going on. These issues look like they were fairly near the surface. We kind of saw most of this starting right off the top in those upper slices and continued throughout. It may have gotten a little worse throughout. So in kind of conclusion of that round of testing, the IE testing was applicable, but really only worked on cool to cold asphalts. What it seemed like to us, around 70 degrees Fahrenheit was kind of the breaking point, somewhere between 70 and 80. And that was not the air temperature, that was the surface temperature. So if you're out in direct sun, it could be a cooler day. You could have those surface temperatures on the asphalt. So if you get cooler than that, or night testing, you can have some luck with the IE test, which is a simpler test for us to analyze. However, you get up to the warmer asphalt layers, and the IE test was no longer working well. And the reason for that is it's the impact that the asphalt gets soft enough that the impact just can't generate those really high frequencies that are going to resonate that pavement like they would a concrete. So the IE test has no problem on concrete at a whole variety of temperatures because the concrete's so hard. But once the asphalt warms up, softens up, it's just really difficult for us to generate those frequencies up there, the 5, 10, 15,000 hertz. The SW test is it's a wave that it's a different type of wave, more energy, better able to deal with the warm temperatures. Higher energies, easier for us to measure and easier for us to excite. So it worked throughout the range of asphalt conditions that we tested. We tested some stuff down in the 50-degree range and all the way up to surface temperatures of 130 or more in New Mexico. And so while those temperatures do affect the velocities that we're measuring in the pavements, we can kind of control or back out from those temperature effects, and and look at the SASW results on a relative basis to detect those anomaly areas. So that SASW method is well suited to detection of debonded, delaminated pavement layers, as well as stripping or raveling. And again, as I mentioned before, the severity of the response. So the severity of that drop in velocity, or the lower the velocity is, or the lower the relative velocity is related to the severity of the defect. So as far as ongoing development, we have kind of continuously refined our cart system. We like the cart system when we're doing bridge deck work. Often on bridge decks, we're typically employing the impact echo method. We like to do it at 1 foot spacings. So instead of trying to get a whole unit on a truck for just a short, usually our typical bridge deck may only be 200 or 300 feet long. It's easier for us to kind of run a single system with the cart and just do back and forth passes. So we found that maneuverability is an advantage on the bridge decks, where because our system is a slow rolling system, we need that traffic control anyway. So we like to have the cart system up on the decks, just going back and forth to get really good coverage of the concrete or asphalt covered bridge decks. We have incorporated GPS into our systems and software, so we're better able to locate the data, which is really handy on bridge skews or pavement, obviously curves or anything like that. Anything that gets complex geometry wise, it's a big advantage. We do have, we can still mount systems to a vehicle. We've lately we've done some wheel path testing, where instead of trying to do 6 passes in one lane and get really detailed coverage, we say, hey, let's just look at the wheel paths and do a single pass, and that way we can cover more ground that way. So our estimated testing rates there with the vehicle mounted system, we can do probably 5 lane miles a day or so. We go about a mile an hour, so depending on how long your day is, 5 to 10 miles lane miles per day with the vehicle mounted system. And with the cart, we typically can cover 25,000 square feet or more in a day. That's it. Those are 25,000 square feet is a pretty conservative estimate with the cart. So we can usually get out there and knock out a whole kind of your whole run-of-the-mill bridge deck, and easily in a day with traffic control in one half and then flipping it to the other half. Even with the vehicle mounted system, because we're doing a mile an hour, we still need that traffic control. Go ahead, next slide. So this is just an example kind of case study result with the implementation of the GPS. This is showing the data results of a large, this is actually a concrete deck with a overlay that we were looking at the condition of that overlay. You can see where the gray is all basically good. The blue kind of vertical lines, those are at the joints. So the joints were showing up as kind of anomalies because they were different than the normal concrete. But then the other areas of more concentrated blue are the areas where they have surface delamination or that debonded overlay. So if you go to the next slide, this is just a zoomed in view of that same data. Again, because we have the GPS in there, we can put it on the available satellite imagery, and you can get an idea of where to concentrate potential repairs. Okay, which lane do we need to focus on fixing? Which can we leave alone? We're also able to tabulate all that data. So in this instance, we tabulated between different joints. The joints for every other span. So we took, each of those sections. We can tabulate. Okay, this much percent was sound. This much was near surface delamination. And so you can get that tabulated result as well as the graphic result. From there, we estimated repair volumes. So assuming a repair, 3 or 4 inches deep, this is how many yards of material you may need. Next slide. A second case study. This is, again, it's a concrete pavement. This client was worried about horizontal cracking in the concrete pavement. They knew that this cracking was there based on some coring and other operations they'd done, and they wanted to kind of quantify, okay, how extensive is this problem? So we went out there and tested, I think it's around 50 lane miles of interstate, and again, which is a single vehicle pass per lane, testing primarily the wheel paths. Some of the testing we did during the day, the outside lanes, the middle lanes, we were doing at night for a larger closure. Next slide. This is kind of two different examples of the data from that project. And again, so this, because it was concrete pavement, we ran impact echo only. So the top plot, really you can look at the frequency plot, and that's kind of the key measurement here, is in that top plot, we get a frequency of about 6,700 hertz. That corresponds to a thickness of that pavement about 12.5 inches. In that bottom plot, you see a large shift in that resonant frequency. You can even see the shift in the time domain as far as the frequency of the response. On that lower plot, we have a resonant frequency of 13,500 hertz, and that corresponds to a pavement or a concrete thickness of only about 6.2 inches. So that's an area where they had cracking, horizontal planar type cracking halfway through the pavement. The plots there on the left, again, that shows one whole scan line about 500 feet long, and it's those kind of the data points off to the left. Those are the ones where we're getting those thin echoes, those cracked echoes, and we notice that they're very periodic. So if we go to the next slide, this is kind of showing those impact echo results on top of satellite imagery again. We're showing everything that's good or sound. It's gray, so it may be hard to kind of see our gray dots on top of the gray pavement, but then the cracked or thin measurements are shown in red. The yellow arrows on the right, they're hard to see, but they're actually pointing toward the joints. So at every joint in this pavement, these cracks were occurring, and it was some interaction with the dowels. And next slide. So kind of going forward, our development, we are still working on trying to speed up the analysis of the SW data. That's kind of our sticking point right now. And so we have different ideas about how to do that. We would like to reduce the processing by a factor of 10 to 100. Right now, we often are reviewing many of those data points individually, at least glancing at them for a few seconds. And that adds up a lot when you're taking hundreds or thousands of data points. So we're hoping to try to look at those on more of a bulk scale, and then identify areas that we want to focus on. So that's what's shown on the right, is that's actually a plot of the wrapped phase. And again, that's about a 500-foot scan line. So it's about 1,000 points in there. And that's 1,000 wrapped phase plots stacked on top of each other with the color showing the phase. So instead of seeing the sawtooths, you see those bands of color. And even just at a quick glance, you can kind of pick out those two areas where I've put the arrows at, that those look a lot different than everything else. So those may be areas where there's a potential anomaly or something where we need to go through and review that data in more detail. And kind of in summary, the applications for the S-Cube system, if we're using the surface waves and NDE scanning, works well on asphalt pavements or asphalt overlaid concrete bridge decks. Could also work on, I know one of the DOTs was talking about having a lot, I think it was Illinois, about a lot of asphalt covered concrete pavement. This would work well on that. It's depending on how thick that asphalt pavement is. It could potentially be that the impact echo method will work really well on that. The impact echo scanning system works well on concrete pavements, concrete bridge decks, and both of those methods are kind of determining the condition of the material by looking at the velocity that's related to modulus. So that the Achilles heel of the system is really the speed of which we can go. I mean, it's a slow walk, so it's 1 mile an hour. We're kind of fighting physics a little bit, whereas the radar, our reflections, we're looking at nanoseconds. These acoustic reflections, we're talking microseconds. So it's 3 orders of magnitude there. So we do have a kind of a time delay where we can't move at highway speeds and still capture the data. We are trying to look at ways to potentially speed that up, but there's physical limits there that we need to go slower. The system does have the advantage of that, again, we're measuring velocity that's related to modulus. We don't have the need for having that potential moisture in those areas of stripping. We should be able to detect those changes in material modulus, whether it's wet or dry. So there are certain conditions where the GPR may have limitations that this tool may be of use to the DOTs. And if you go to the next slide, I'm happy to answer any questions. And we'd certainly be interested in working with the pool fund study and trying to progress the state of the practice.
Okay. Thank you, Pat. Anyone have any questions for Pat?
I have a question, Steve.
Yes, go ahead, Ian.
Pat, this is Ia from Minda. Thank you very much for the presentation. In our current auto process, we're thinking to basically collect very long data, 5 miles, 10 miles using the GPR and hopefully the TSD. And then on area identified by the GPR image, conduct more investigation, but small scale investigation using other spot type test, impact echo and SAS SW, SW and other. Do you think that's a good approach, or do you have any comment on that? And then related to that, you showed that in your data, you saw that using the velocity normalization, it somehow offset the temperature impact to enhance your images. Do you but still we're not able to test at high temperature. Is that correct?
So the first question, that's okay. The first question, yes, I think that's certainly a great application. Again, the GPR certainly has the advantage of going much quicker, covering a lot more ground than our system. And like you mentioned, but if you identify smaller areas that you want to take a more detailed look at, then this could be a complementary tool to go and get some additional information for. So I definitely think that's an excellent approach. Regarding the second question, the SW system works well at the full range of temperatures we've tested so far, which included very hot pavements in New Mexico. So the SW doesn't have any limitation on temperatures. It's really the impact echo method does when it comes to hot asphalt, it does not work very well. So that's why we really recommend on asphalt pavements, we recommend doing the SASW testing.
Oh, I see. Okay, so thank you for that clarification. So the SAW does not have any, is not affected by temperature.
Correct.
That's good to know. Thank you.
Anyone else?
This is Larry Olson. I was just going to add to Yob's question that it's important to note that the surface wave method and impact echo don't require the stripping or raveling to be filled with water. It's sensitive to modulus. So might be a reason to do a little more testing with it even, just for where you're concerned that the conditions weren't ideal for radar.
I see. Thank you.
Thank you, Larry. Okay, Pat, thank you for your presentation. And we'll move on to our last vendor presentation for today. And it's by Road Scanners, by 3D GPR by Timo Sarankato.
Okay, good evening or good night, everyone. It's 10:30 p.m. already in Finland. So I'm happy to talk here and talk and I'm was planning to give you a little bit overview about a little bit about history about moisture related damages in asphalt pavements and Steve, if you can give me a next slide.
Yes.
So starting when now this session is very much Minnesota oriented, so it's good to start from the Minnesota. This is from the year 2000 when we did the first work in Minnesota with the stripping and Trunk Highway 23 in Wilmar. And what you can see here is stripping bottom up stripping and these transverse cracks, and on this dark blue on the top is a GPR data, and on the dark blue you can see also that the stripped velocity or dielectric value of the stripped material when it's wet, so it's much higher, so you see peaks down, but when you do the correction with the distances, so which is on the lower graph, so then you see but very typical stripping what we've been working, which is full depth asphalt lying in a wet subgrade, and it's a mechanical damage very much related to the dynamic loading and water breaking the binder aggregate bonds. Next slide. And since that, what we found already in Minnesota more than 20 years ago, that one interesting was to confirm stripping was deflections, as we've been hearing already. AOP showed some data, and that is really what we've been finding everywhere. That it's for instance falling away deflection balls are not like typical round deflection balls, but they are very like they have a strained curvatures and everything else, and look a little bit strange, and by analyzing that you will always get an indication where you have a if you have a severe stripping. And next slide. Then the next case about stripping is from Scotland. Few years beyond, I think this is from 2005, and now we have a concrete road, actually very unorthodox concrete road building over a moss or peat bog in 20s, and then overlaid with the asphalt, and once it was exposed to the heavy traffic, it very quickly started to have a major stripping problems. And what you can see here the really clear a reflection on the stripped and on sound asphalts, and this is also quite typical. So in that way, I would say that working with the GPR almost 40 years, so stripping in typical stripping is pretty easy to detect when you have a hint that okay, there's a stripping, so you can find this and correlate the strip layer with the drill course. Next slide. And here is another example of, and if you click once, so what you see, Steve, the next slide, and click one more time, and here's a transverse crack, which is also very much related again, like a bottom up cracking stripping, and if you click the next one, and it comes from here, and you see really the main reason with the stripping is the moisture on the bottom of the asphalt layers. Next one. Then we started to use on the stripping or moisture-related problems. We started to use, so to say, semi-3D moisture analysis, and this is from Poland about 10 years ago. And in this case, we used pulse radars, but several passes per lane and road shoulders. And then we made the moisture analysis. And on this case, what you can find also at that time, we found also on the 2 gigahertz data and coreless data when we are using 2 antennas and using velocity analysis. So we found a clear correlation with the high moisture content in certain layers. This was a typical moisture trap and K2 lane, so passing lane, not so much related with the heavy traffic, but just a very typical case of a moisture trap. But worked very well, and it was confirmed with the drill core, and all the rehabilitation works were based on the GPR data. Then in 2000, next slide, and we've been hearing a lot of GPR data, and I can tell that this is one of the first GPR data. We were the first company started to work with the 3D radar. I think it was 2005, and at that time started to test with the different applications, and since that we've been testing different antennas, and next slide will be about segregation. And here's an example of ground coupled new 3D ground coupled analysis about paving quality, and we are right now working with detecting segregation also on the new asphalt pavement. So thermal camera data is on the top, where you see these blue ones, which are cold, about 100 Celsius degrees paving temperatures, and then over there you see the time slices on the 3D GPR data, starting from the surface, going to 6 millimeter, 1.2 centimeter, 1.8 centimeter. And if you, Steve, click a little bit many times, you start to see here also, this is automated, so it shows how it goes deeper. And what we've been finding out, what is really interesting, that many times, like segregation in asphalt, you think that the segregation is worst in the surface, but with the 3D time slice analysis, with the ground coupled, detailed ground coupled, you'll find many times that actually the worst segregation is on the bottom of that of this new overlay.
Are these
Next
horizontal
slide.
slices, Timo? Sorry, are these horizontal slices or longitudinal?
They are horizontal slices. Yes.
Okay.
Yeah. And the next one. And next one. Okay, and one more time, if you click. Okay, then this slide is, and next thing what I'm telling you, probably not all of you don't like too much, but over the last 5 years, we've been doing extensive testing with the 3D radar, ground coupled and air coupled antennas, and based on this test, we have ended up to recommend and started to use ground coupled antenna. It is because it is so much better when you are doing asphalt testing in close to the surface, where you need to really find detailed cracking, when you need to find stripping and other things. And of course, the issue with the ground coupled is that you probably can work and collect the data with about 25-30 miles per hour, and in that way you need to have a protection car. But on the other hand, our customers now, when they see the quality, so they are ready to pay the protection car and arrange the traffic because of the data quality. And this is our road doctor survey one. Also, what you can see also in front is GSSI system, a little bit similar that AOP already showed, because pulse radar is also giving some information. It has a certain advantages compared with the 3D radar. So when you collect both data, so then you get much more comprehensive like analysis data based on to support your analysis. Then we have a LiDAR and 360 cameras and IMU where what you can make the model. And the next slide. And with this system, what we've been doing is quite much now over the last few years with the moisture-related analysis. And here's one example from Central Europe, one country. And again, you have a full depth asphalt motorway, very busy motorway, full depth asphalt with the 6-inch of layer 1 and 6-inch of layer 2. And first is a longitudinal profile with the 3D radar. Then on the next one is a LiDAR remission data. And then the last 3 colored scale is moisture analysis data from the layer 1, and what you can see on the top profile, and the moisture analysis of layer 2, and then a little bit about combined analysis, where if you want to have only one map of the detected moisture. And what you can see here is a very typical problem also over there that can be related to the segregation. So you see even spaced moisture damages on these sections, and so it's like a load related segregation. On the other hand, you see also anomalies on the road shoulders, and I'll come back a little bit later. In this case, the layer 2 was pretty sound, and we couldn't find any problem, so it was on the top layer. Next slide. And here is a little bit worse case. So now we have a big issue with the segregation in the layer 1 and even spaced, and also now it's also on lane K1 is also a certain part of the moisture related. In this case, it was a pretty severe damages on the customer side also. And now you can see also on the layer 2 was in this section had issue, and a little bit on the layer 2 you can see also some some damages that you could even relate to the wheel paths. And next slide. And this is a photo, I think, very nice photo. What is right now going on, and discussion with our maintenance that should we, if we have asphalt that is susceptible for stripping, so should you wait until you have a stripping and you have to mill it away, because stripping, it looks like stripping doesn't take place if there is no moisture. And for instance, in this case, you can see, first of all, on the top part, this arrow tells you that you have a verges, you have a soil verges or crash verges, and because that water cannot go away from the pavement, and it is infiltrating into the pavement, and sooner or later you start to have a stripping. On the other hand, on the lower part, there was central lane with the guardrails, there were areas with the water ponding or pooling, and the drainage system didn't work. So instead of like starting to detect stripping, you would the idea is what we've been discussing in Europe in many countries, that you should start to find the area where the water is going to the pavement and start to work with the drainage system, because then you can probably you can buy 10 more years to keep the system dry, because most of the cases stripping needs water. And if you don't, if you keep the drainage system okay, you don't have a stripping problem. So next slide. And that's the last slide what I wanted to show. So this is our new system, what we call a Road Doctor Digitizer, where we have a 3D radar under this trailer. GSSI system also is there. You can see the red boxes and LiDAR, IMUs, and 3D 60 cameras. And why we developed this is to work with the transportation issue, as we heard earlier also, that hauling this, for instance, in Europe, this is like a transformer robot that you just flip and 30 minutes it is a one container, this whole system, and it's a standard aircraft container, small and container box, and then you can rent a car and go to one place. So within the Europe, you can transport this box in one day, and then it's about 30 minutes and you are ready to run. So it's very quickly, you don't have to mount it to the special vehicles. Next slide. And here's just one last example about this moisture related diagnostics that we've been working on, this tuning on this analysis, and very much working on this frequency related analysis. This is also benefit with the ground coupled, because if you have a ground coupled antenna, the energy that you are putting to the pavement is very constant. Our antenna is only a few millimeters above the pavement, so you can trust that all the energy is constant. Once you have air coupled, it's always bouncing, and as we heard that on this pilot, we should use probably only one system to control that you are getting similar data. Here's a case of quite new data, sound area, and if you click, the next one is what you can see, drill core from that area, that section. Now you see also debonding on this one areas, but if you can analyze debonding, you can do that also, but it's not. You need to have a different algorithm compared with the moisture. Next slide is how we are now putting classifying slightly damage or slightly moisture content, what we call medium moisture content, and if you are taking the next slide, you can find the drill core, and here you see partly, and this is like a warning right now, that once you start to see that, you should go. This is again on, if you look, show the previous slide again, so you see that this is related from the road shoulders. So there's a verge. You should go and should tell the maintenance crew to fix the verge. Don't allow the water going there. Quick the drainage, you save a lot of money. And then the last one is the what we call severe moisture, where you are starting to have probably early phase stripping, but not yet, but you really need to do something. And if you click that, and take a drill core. So it is in this case we had about 23 drill cores, and the match was just perfect. So we are really happy with this early phase moisture detections. So that was pretty much what I wanted to sell. So I guess the last slide is here. Also on the work what we've been working with this system is very much now on the airport, and this is from Toulouse Airport, which is the home of Airbus Industries, and with the Airbus they have a very heavy aircraft and very interesting pilot place to test the models also on that side. So that was my message to you. So thanks.
Thank you, Timo. Anyone have any questions for Timo?
I do have one too.
Go ahead, Ian.
Timo, thank you very much. And thank you very much for hitting also on an important topic, the 3D ground couple. Yes, yeah, that is an important. And I want to comment that 3D radar or Contour has graciously lent us a 3D ground couple study for a limited time to be, and we're hoping to look at the 3D GPR ground couple and air coupled just for us to compare and see how much of that information or what type of information we are losing by not using a 3D ground couple. So that is one thing. And I will also take the opportunity to thank you both, Road Scanner and Contour. You guys it's been an absolute pleasure working with you. You always respond and address our questions quickly, and you provide all the training. With that, you did show some moisture stripping images there. Is that part of the package that we have, that software?
No, these last slides are brand new. This is our just under evolution now, and we are testing with the different big PPP asphalt companies in Central Europe, and we are still testing and developing. But it will be in the Road Doctor 3D,
okay, and hopefully
3D
this
radar
fun
package.
study could be part of that validation and testing too. Okay,
yes,
thank you very much, Timo.
Okay,
thank you for standing up late.
Thanks.
Yes, Timo, thanks for staying up so late. So anyone else have any questions for Timo? Okay, hearing none, let's take just a quick break, like 5 minutes, and be back in 5, and we'll start into the next part of the peer exchange, where we'll talk about an open discussion with all other state DOTs that haven't talked, that might want to say something about what they're doing, what their experiences and challenges are, and then looking at future action items to pursue, and where we go from here. So let's take a quick 5-minute break, stretch your legs, and we'll be back. Start up again. Okay, everyone, we're ready to start again. I'd like to try and do a couple Mentimeter polling questions, which would help not only us for this event, this peer exchange, but might help EOB as well with moving forward with his pooled fund study. So what I'll do is I'll share a link in the chat for you to respond, and then I should be able to share the results on the screen. Okay. Chat. Let's try this and see how this works. And this is anonymous, so it will just give us the results. So go ahead and enter that website and use that code. Okay, it looks like we've about stabilized with respondents. So majority is experiencing frequent moisture-related damage or stripping, and it's widespread. But it's only about 15% off from what's infrequent. So thank you for that. And we will go back to the next question. And this is open-ended, so you can type in your answer. Mm. Okay, we'll end the polling at this stage and come back to it if we have enough time. But I want to get to the next phase of our peer exchange. So I'm going to turn it over to Brian Prow. Brian's going to start the discussion. Brian, do you have anything that I need to turn the controller to you?
Yeah, Steve, I was going to type some of their answers and share that screen if that works for you.
Okay, I'll stop sharing. Okay, were you doing that in the chat phone? Oh, I see. Okay, go ahead.
Yep. So good afternoon. Really good discussion, good presentation so far today. Not all the states had the opportunity to present, and I think maybe listening to some of the other states' presentations or some of the presentations since, some other topics may have come up. So we kind of wanted to start this with an open discussion of things you feel we haven't discussed, or things that you recognize in your state now that you hadn't thought of previously. So this can be for either states or vendors, you know, whatever's on your mind that we should add or consider in the study. Any ideas? All right, not hearing anybody want to add to the discussion or bring up topics that haven't previously been covered. Maybe we'll hold on that one for a moment and talk about, see if there's any comments on challenges of using NDE systems to detect moisture damage in asphalt pavements. Challenges you've seen from the presentations or your own experience collecting data. Don't forget to unmute yourself. One of the ones that came up in several of the presentations was managing the size of the data files and the amount of data collected. Has that been experienced by any of the, either the vendors or state agencies that have collected data so far?
This is Jerry DeLyden from ARB Systems. We collect, I mean, I don't even want to pretend to put a number on it, huge files, and have been for the past 5 years. And for the 30 some odd states we've been collecting information for, none of them seem to have that big of a problem with it. I think it's not the size of the files, it's the ability to get to the nuggets that they can apply and utilize. I always make the joke in all my presentations when we're delivering data, you know, my wife has a terabyte server just to store all of our grandkids' Disney movies. I mean, data storage is not an issue anymore. But you know, the reality is people aren't paying just to get data, they're paying to get answers. And if you can't extract the answers out of the data, that's the real issue.
Thank you, Jerome. That makes a lot of sense. And I know several of the equipment vendors have been working on analysis software, and EOB mentioned that that's one of the goals of this study. Any other thoughts on either flowcharts or systems of analyses or software to kind of guide that effort?
Brian, this is Ken Mazer with InfoSense.
Go ahead,
Ken.
Ken.
Yeah, just to amplify what Jerry says, the files are big. You know, they turn out to be multiple gigabytes, a lot of them. But it seems that if you kind of accept that and set up a file transfer system that manages that, it's not a problem. So it's just important to recognize that and set up a way of transferring files, which I think ARB has already done and very effectively. And then once the data goes into Examiner, for example, the software has no problem with the big files, and very quickly you can extract the useful information, and then the file size doesn't become an issue anymore.
So, Ken, I'm guessing from that Examiner is designed in a manner to handle the database so it doesn't get bogged down. I know, you know, using spreadsheets and things with large volumes of data, they tend to get bogged down, and you struggle even to scroll through the data.
Yeah. Now, Examiner seems to be well designed, and I think early on, the folks at Contour recognized that they had to address this issue, and I think from what I've seen, I've been working with them for about 10 years now, and they've quite streamlined the whole ability to handle these data files pretty well. So it doesn't bog down. And then when you analyze something, you've got reduced data, and they become more like spreadsheets, CSV files, or things of that sort. So it's a lot more manageable.
I'll pose a potential challenge, and anybody can chime in if they believe it's correct or not. But what about having the expertise to interpret the data, to work with the software? Do you need proper training? You know, is a very limited audience of folks who are capable of doing that. And if you're trying to get new folks that have never experienced this in a state DOT, do they need any assistance or help and training and education expertise to be able to pull from the data the valuable information? I know you say, Ken, you're saying the examiner software does that for you, but is it intuitively obvious enough to the new beginner, or is somebody else need to assist them or help them at first? Is there some training needed or something?
I would think there is. It's taken me a while to kind of figure it out.
Yeah, everyone on the call today seemed to be in this for such a long time. You know, you heard Timo say 40 years he's been working with it, and others have been working for 20 or 30 years. So, you know, new folks that have 0 to a year or 2 of experience might need some help, is what I was wondering. And I just wanted to see what others thought of that.
Yeah. I would agree.
If I can also intervene in the meanwhile, as you know, providing Contour's point of view. Let's say that three-dimensional GPR can be a little bit easier to read or to understand once you see somebody that has interpreted the data, like, for example, the data that Timo has been showing and that Ken Mazer regularly shows. It becomes a little bit more obvious once you start to see those depth slices, right? So you see something that has a shape. This doesn't mean that analyzing in depth the data is a piece of cake. It requires a little bit of expertise, and especially in understanding what is a positive and what is a false positive and what is a negative, right? And that in short, that builds up confidence in understanding the data and being sure of your analysis. All right, that is going to take time, like with every tool. On our end, we as manufacturer, we strive to go into automatic analysis. You know, that would be excellent. But we also know that is going to take quite a bit of time. You know, the more people we have analyzing the data, the closer we can get to an automated analysis. And this is, if you think about, for example, how much pavement can change, I don't know how much the response from pavement can change. That tells you, you know, it's not all asphalt look the same, obviously, and that's the same in the data. Not all data look the same, and therefore it becomes a little bit more complex, or can be very complex, to build up some automated tools. But we can work on replicating what we do well. So, you know, on semi-automated analysis, and also to make the data a little bit more available. And that's why also we are trying to make a little bit more transportable the result of interpretation. So once, you know, InfraSense or road scanners have done some analysis, or people that is skilled in interpreting radar data, we want other people to be able to access the result of interpretation and still provide an interpretation on top, because you have radar data, interpretation based on radar data, and then diagnostics based on the interpreted radar data. And that's what we are trying to give. You know, the simplified part at the end should be way more available to a wider audience. And I can bet that part there right now can be transferred to every single person in this audience, for example. I think that after the interpretation of radar data, you can take that interpretation and then build some diagnostics on top of it. So you can have an opinion on how the pavement is looking, right? Because I think also that layer there is very important. How do you interpret the interpretation of the radar data? So once you extract important and meaningful features out of it. And the three-dimensional system, I think, is a pretty good key to recognize the geometry of features and objects and whatnot in the pavement. So that's a lot of what we are working on. And I think that's what also Ken was mentioning in some other presentation that he was doing, you know, in terms of geometry and understanding the nature of reflections.
Brian, this is the
Oh, sorry. Go ahead, sorry.
Okay, so this is just coming to my mind is I think from the R06D, I think we learned of Minnesota, we learned is we need to probably better define this severity level of stripping. I guess we need to understand limitation of GPR and what size of the stripping we can detect using GPR, what size we cannot detect. I mean, we made Mike knows they made this made the stripped sections and NCAT that showed up very well on the 3D GPR, but not every stripping and real world is just like that. Sometimes it is not very obvious, and so but then how do we using GPR effective to detect maybe slightly stripped asphalt? Or versus the severe stripped asphalt. So I think it probably go along with the Jacques talk about the data analysis and how to refine the data analysis method or improve the software can be able to allow user to better understand this limitation of the software in terms of pickup stripping level, severity level.
Brian, can I add one more challenge, practical challenge that we have here? While we have Jacopo and Timo still up. So for us, we've been collecting a lot of data using the road ductor system, and one way we have tried to solve our data storage problem is by using by creating our own NAS Synology server. And once we finish processing the data, once the pavement is repaired, basically that data is quite not useful, so we get rid of it. But one challenge that we've seen is once you have processed your data, GPR data, most of the times, I mean, the image speak 1,000 words, but it's very hard to basically provide data, all that data, processed data to the customers, I mean, to the engineers. One reason is because most of the times if they have to look at it, they need to upload the software. I know Road Doctor has a user only a review software only for review, but still that is a kind of a little bit sometimes with all the things that you have to do to open a new software, understanding it. So it's quite very difficult. The other one thing that we are doing right now is basically once we finish processing the data, we create a video screen of the data and then we show it through YouTube channel. And so I don't know if the vendors can work on this, on how to an effective way of providing the data to the end user without having to have softwares, or because right now we do have only one software for the research office. So I don't know. I would like to hear some of that discussion having place with the vendors.
Okay.
Does it make sense?
Yeah. Can I answer? This
yes,
is Timo. Timo, yeah. Thanks, Eyop, and thanks, Jacopo. Yeah, it is a problem, and the big issue at the moment. What we have been hearing is comments already today that we should have a standard how to process the data and everything else, and then you can have a like a transparent procurement process. But how can you make a standard with the system that is its evolution? It's going through very fast evolution at the moment. It's improving all the time. And what I'm really afraid in that if you are making a very fixed standard, even with the GPR, then you are freezing the development. And so that's one. But then on the other side, answering to Eyop's question is that this is really an issue. We've been testing that if you give a free viewer version, or if you get the GIS-based mapping system, or what is the best solution on that? And we have seen tonight quite nice examples of different solutions. And my opinion is that GIS with the background of with the satellite images and everything else, this is probably the solutions. What we've been doing here in Finland is at the moment that we are already bringing this data to automated machine control system, which is the next step. And for instance, we've been hearing quite nice comments about, for instance, the milling depth, and how do you program the milling depth, and that is one issue. Of course, another issue is drainage and others, but this is the future, and I'd like to a little bit warn you that with this work and this project, what we are discussing at the moment, that you shouldn't rush too fast to make a very like a harsh fixed classifications or other rules how you should do, because our software is developing, our hardware is developing, and they are coming more like better and faster, and also easier to understand. So in that way, we should be, if we are making specifications or standards, what we should do is make these standards in a way that they are enough flexible to not to like like break down the development, because this development will be in the future, or it will be going really fast in the future. Okay, thanks.
I very much agree with your
time out. Hold on, yeah.
Timo. Oh, sorry.
Yeah. Hold on a second. Steve Cooper, do we have someone from FHWA to talk about the new technology manual and website today?
Hoda, are you on?
I am on, yes.
All right, so we're going to pause this discussion and allow Hoda to talk about the NDE Info Technology Manual and website.
And in the interim, Brian, can you look at the chat? There was a couple challenges that were identified in there too.
Awesome. Thank you, Steve. All right,
yep.
Hoda.
All right, thank you. So let me share my presentation. I have a very quick presentation, and then I'll do a live demo. So, okay. Just can someone confirm you can see my presentation?
Yeah.
Yes.
Okay, perfect. So good afternoon, everyone. Today in my presentation, I will give a quick background on the Info Technology platform, which is a web-based platform that assists state DOTs, asset owners, practitioners, and users to select the right technology for their application. But before I do a live demo, I would like to spend a few minutes on the challenges, the different types of NDE technologies, the challenges, and also like the objective of the Info Technology platform, and why Federal Highway developed a web-based manual like the Info Technology. So we have, as you know, we have a few or various NDE methods that they rely on physics to be able to sense problems. It ranges from mechanical wave to electromagnetic wave, and so on. So we have a variety of NDE technologies, and we have a list of different applications for NDE technologies for quality assurance of new construction and for condition assessment of existing and in-service structures. So as you can see, there are a variety of NDE technologies, and there are numerous applications for these technologies. But there is a lack of unbiased information, there is a lack of guidance and proper selection of NDE technologies, and there is a lack of confidence because of the vendors over-promising on technologies. So to address some of these issues and challenges, and to actually fill in the knowledge gap between asset owners, practitioners, dealing with highway infrastructure challenges and performance challenges and applications, and researchers and technology developers developing these technologies. Federal Highway Administration developed the Info Technology web portal. It is a web-based tool to assist asset owners and practitioners with proper selection of NDE technologies. So in the current version, only steel, concrete, and timber bridges are included. Also pavement and tunnels are included. So, but in the next version, more technologies beyond NDE will be included, like structural monitoring and sensors. Sensor technologies will be included. Also, we are planning to include technologies for underground utility detection. So now let me give you a live demo. So Info Technology is a module under Info Highway. So if you just type down Federal Highway Info Highway, it takes you to the main website. It has the Info Pave, Info Bridge, Info Material, and the last module is Info Technology. So if you go to the Info Technology website, as I showed you, there are technologies for steel, concrete, and timber bridges, for asphalt and concrete pavement, and for tunnel. So since the focus of this meeting is pavement, we go directly to the pavement. So here on the right, you see all the technologies that are applicable on the pavement, no matter like the material, the target of investigation or application. So these are all the technologies. And then the user can narrow down the search by selecting the type of the material, for example, asphalt, and the target of investigation. For example, if we select delamination, so these are the technologies: GPR, impact echo, infrared, and surface wave. And if you click on one technology, for example, GPR, you see there are 3 tabs here. The first tab talks about the technology, the GPR that you selected. So it starts with target of investigation, like what GPR can detect. Description of the GPR, different types of the GPR technology, air coupled, ground coupled, and physical principle of each type of GPR. How to acquire the data, how to process the data, and finally how to present and interpret the data. And at the end, advantages and limitation of the technologies with a few references listed here. So these are all written in very simple words, so that the user shouldn't have like NDE expertise to follow the sections. It's very user-friendly. It has a very user-friendly interface. The second tab is target of investigation. For example, we selected delamination. I know here is a description of delamination in a bridge deck. But here, the image at least is from a bridge. But here's a description of the lamination and asphalt pavement. And then structural element, it talks about like the surface course in asphalt pavement. If you come down here, these are the technologies for delamination. You can select another technology like impact echo, and similar to GPR, it starts from the target of investigation, the description of the method, and so on. So again, in very simple words that you can follow, like what is the physical principle behind the method, how to acquire the data, and a few references here. And if there is any standards, we try to list them here and in the references. You can, if you want to just save this information on your machine and refer to it later, you can export it as PDF so that you can have a PDF version of all the technologies that you select here. This is like user-friendly, very practical feature of the website to save the information that you want to refer to later. The library, it has the glossary of terms and acronyms and abbreviation. So if you're an asset owner or manager and you're not familiar with the terms, you can search the term here. For example, IE, it is impact echo. So if there is any acronym that is not defined in the text, you can refer to the library and find what it means. And here is a list of abbreviations. So that is a very quick demonstration of the website. If you have any questions or if you have any suggestions to make any improvement to the website, if there is any technology missing here or any target of investigation missing here, please reach out to me. It's a live document. We always update the website, or we try to update the website frequently. So if there is anything missing, anything that you feel like we have to address, please reach out to me.
Thank you, Hoda. Any questions for Hoda?
I don't see any in the chat that are questions for Hoda.
Thank you.
Thank you.
Thank you.
Darlene, can I add a comment?
Certainly.
I was looking at the website, it's really nice. On the soil, on the non-destructive technologies, we've been using a electrical resistivity tomography for some projects. It's really worked nicely to help us with some some moisture problems with perched water tables, and then we used it to find some scour debris when we were trying to relocate bridge shafts. So that's another non-destructive tool that we have found useful, and we're finding more uses for it in the highway applications.
Thank you, Darlene. Can you send me this information? What would be the target of investigation? What was the application for?
We looked at two things. One, we were looking for water tables that were close to the surface so that we could see if we were going to have moisture problems when we widened a freeway. We used it to look for caves in an area around Austin where they were going to lower the roadway, and then they had to build some drainage. And so we were looking for cave formations. And then we also used it to look for some rubble and other debris that had been used over the several years by maintenance to fill scour holes. And then we were widening a bridge, and we couldn't, we had to move the bridge foundation because we couldn't get rid of all the boulders and concrete rubble and other stuff that was in the way. So So we found some interesting uses for it. We really like it.
That is perfect. If you can send me this information or any paper report that you may have, we can certainly add it to this section.
Okay, I'll send you some stuff. And of course, everything we've done with it so far has been for TxDOT. So
Okay.
I'll check with, I'll copy them on anything I send you so that
Perfect.
they'll know.
Thank you.
Okay,
thanks.
Yeah, Larry Olson here. I might add a comment. One of the things that's challenging is when a non-destructive method or is it a geophysical method? And Darlene raised, we do electrical resistivity topography and a whole range of geophysics for transportation projects, but there's also within FHWA an emphasis on this. So I would just ask Hoda to check into that and see if there's a similar website already and something to.
There is.
We work in both areas, but I just don't want to blur it, shall we say. Fair enough?
Yes, that's right. Yes, there is a very similar website. I'm not sure about the status of the website, whether it's still on or if it's updated recently, but there is a very similar web manual website for geophysical applications. Yeah.
Thank you, Larry. Eob, you had a comment earlier that I put you on hold for so we could let Hoda present.
Yes, thank you. I wanted to circle back on Timo's comment about the specification and standards. I understand his concern, but what we're trying to do is not an open-ended specification for general use. The specification and the standard will be for basically, if you want to use this technology for detecting stripping, then you need to be testing at this ideal condition. We need to come up with those ideal conditions. We need to come up with what speed, what type of calibration you need to do. And then we need to be able to give some confidence level. If you do all this, if you test at this condition, then this is what you're going to what you're trying to get. That is important because most of the times when we talk to engineers and to other end users, they need to know how sure we are about our prediction. And without standards, without specification, without a certain way of doing things, it's going to be difficult. So I do understand his concern. This is not going to limit the evolution of these technologies, but this is just going to provide additional tools for engineers and end users to build confidence on these technologies because they will have them backed by a standard, by specification. That will also evolve with time, the more we know. So I hope that addresses his question, his comment.
Great. Thanks, Eob. I totally agree with you. My fear is experience on working more than 60 countries, almost 70 countries in the world, and it looks like USA standards are like almost like a Bible in the world, and I've just last year faced, for instance, one standard that is explaining that you have to use analyze with the computer tools 86 and PC, and that is the problem. So if you are writing method descriptions and standards, make it flexible enough that it doesn't hinder the development. That was my fear.
Yes, very good.
This is Jacopo from Contour. If I can just add one thing that was, it's unrelated to the very last two sentences, but is related to what Eob was asking, and then Timo answered. The availability of software and stuff and training in general. Of course, we do training. I just want to let everybody know that we do training. We follow up with existing customer and users, or just people that is curious about the technology. I think we are pretty open-minded in talking about GPR, not only ours, in general about the tech. And also we anybody can download our software and install it as a viewer, at least. So even if you're not going to process radar data, you want just to see the results, the interpretation, the process data, etc. So something that is going to be shared, I suppose, within a group like this one. You can download our software and install it. You don't need any special license for that. You just need the link and to register yourself. And I promise you're not going to be spammed, at least not that much. All right. Just wanted to let everybody know that Examiner can be downloaded and installed by anybody, and anybody can get in touch and ask for some training or just discuss the tech.
Hi, has Brian finished his list of challenges, or are we still working on that?
I actually never started the list of challenges, Tom.
Oh,
but
what was the one before
actually,
that?
we did get challenges. We didn't get action items. We did get challenges. If you have other challenges, we can add. Certainly.
Can I give one challenge, talking from experience? Like Timo and Ken, I've been looking at this application for quite a long time. And I know from their experience in Texas, you've got to be careful. And what you're trying to avoid is minimizing the risks of false positives. And, one of the things we find is we come up with rules for how to interpret the data, and this is the patterns we're looking for, and we think that's stripping. That might not be the case. There are several naturally occurring materials and mixed designs which are inside the pavement, which may give you the same pattern as what you're looking for is what's stripping. So don't go, the term automatic interpretation scares me. We do interpretations, but we never, we always call. You always have to pick, this is the spot. Maybe it's a 10-mile project and you only have to 1 or 2 locations, but you have to call and validate and not sure you're messing with some strange material like slag or various other things which give you the same patterns. So automatic processing scares me, and don't ignore the validation coring. That would be my message.
Thank you, Tom. Anyone else have any challenges before I turn back over to Steve Kozer?
Yeah, Larry Olson here. I guess I would just mention, I think it's already been well presented by Pat, that one of the uses of the surface waves in impact echo would be as a second and non-destructive method for validation as well, as already indicated, is being thought of in the pooled fund study. And so certainly the pooled fund study will be addressing a lot of these issues, but integrating it with something to check it is a very good idea. And we have done 3D GPR on both pavements and bridge decks with the system, less so than many of the others on the call, but we have used it in our company as well.
All right, Steve, are you going to run some?
I want to do some customer satisfaction questions before we lose too many people here, since we're already over a little bit. So I'm going to use the Mentimeter polling software again. There's only 4 questions here, and I have a different code now for you to use, but I think when I present it, you should see it. So you just go to Menti, www.menti.com, and get the share up here. Can anyone or everyone see that now?
Yes, I can see it.
Steve, Larry Olson here. As a vendor and consultant, you probably don't want us answering this, I assume. Are you strictly looking for DOT participation?
I think we were looking for all participation for the virtual peer exchange today.
Okay, that's fine. I just wanted to check.
Okay, looks like we're pretty much stabilized here. I'm going to go to the next question. Asking what did you like best about today's peer exchange?
Steve, do you have a new link or is the old one?
This is the newer link. This is the second link. See it up here, 26493196 is the code.
I see.
Okay, we'll go to the next question, which you probably obviously can guess what it says. What did you like least about the peer exchange today? Okay, and then I'll move to this last question, Larry, is really for the state agencies that participated today. And if you don't want to share it here, you can email me directly if you feel uncomfortable in doing so. Okay, well, I'm going to stop the poll now and thank everyone for your participation today and for hanging in there, especially the state DOT presenters, EOB included in there with his 2 presentations, and all the vendors for their time and effort in presenting, and the folks that helped me, Brian and Jeff and Dennis, appreciate it very much. And I would just like to turn it to Steve Cooper if he has any closing comments to say, or Tom or Hoda. I like the
Yeah, I tell you, Steve, it's been some great information. Seems like it's a long virtual day, so I don't want to talk more. I think you did a great job, and thank you.
Okay, thank you. Okay, everyone. Well, we will get back to you. For those of you who wanted the PDH credits, remember that the chat has the address there for you to go complete the form, and then we'll get back with you with that, and we'll plan to send out a notice once the video is available. And there's a couple presentations, specifically the one from Kansas that we could not play, that you'll be able to have access to. So let's see, did somebody just send something here? Jerry, thank you. Okay. What was the code again? Brad. Are you talking about the code for the poll questions, or for the
Yes, for the poll questions. Sorry, I had to step away and then I came back.
Okay.
He was gone. Thank you.
2649-3196. Okay, thank you all.
Please.
I'm sorry?
One more time, please.
2649-3196.
Thank you.
All right, thank you. Okay, everyone, have a good rest of your day, and we'll be in touch.
Thank you, Steve. Thank you, Brian. Thank you all. This was a very good discussion.
Yes, thank you.
Thank you all. Yeah, thanks, Steve.
Thanks, everyone. Well, don't forget to end the recording, Steve.
That's what I'm doing right now. Thank you. Yeah, I don't want to have like 20 hours of recording.
Yeah.